All right, so why don't I go ahead and start with, and these last few guys will sputter in. All right, ready? Cool. Welcome to Python Beyond the CPU. I'm Andy Terrel. I'm going to be giving the first or most of your lectures today. I'm going to pass off the floor later to Travis Oliphant, who's over here busily writing his slides. I didn't mean to write you out there, Travis. So just to kind of give you an idea of who I am, I work at the University of Texas at Austin. I'm a scientific programming professor there. And I work on, right now I guess my big application is on surge water flows, doing tsunamis, and helping scientists who want to speed up their code to massive order. So doing things like real-time modeling of tsunamis to get early warning systems. I'm also an advisor at Continuum Analytics. So anytime a Continuum Analytics product comes up, just like to make sure you know that I am affiliated with that company. And the resources provided today are provided by the Texas Advanced Computing Center, which is a NSF-funded supercomputing center. Believe it or not, your taxpayers go to run machines that have been running for many years, and TAC has graciously given us one of their GPU machines to use today. And so that's kind of, those are the affiliations, who we are, and what we're doing. I think everyone has this, but if you want to get on the account, you have to get account information from Ben. Do we still have accounts left, Ben? Awesome. So we have a bunch. All right. Yeah. So the other thing to know is like the slides are at this bit.ly. My slides are, because they're written, are at this bit.ly link right here. And feel free, there's a lot of details in these slides. I'm a professor, which means I'm paid to speak a lot, and so I often just throw in lots of details. If you get bored or something else, it's nice to have the slides to kind of go for it. So it's just bit.ly/PyCon GPU with funny capitalization because I wasn't thinking. All right, everybody got that? Anybody not got that? All right. Cool. How's the internet working for everyone? Is it working? It's slow, but SSH works, right? Good. Yeah, don't be doing any X server or VNC clients on my machine because that'll bog down the internet for everyone. So if we try to keep, if we play nicely and do SSH clients, we'll probably all be able to use the machine very effectively. And so just a request if you're going to start doing it on the machine. Yes. And just to be, and also don't run any password crackers, DDoS attacks, or anything like that while you're on my machine. We do have security professionals watching the machine, and they will shut us down if somebody starts playing badly. But just to throw that out there. I was asked to make a few announcements. First one is there's a 20-minute break halfway through, so you have an opportunity to break out and go somewhere else if you think I'm too boring. And that's going to happen at 1:20? No, 2:50. There we go. I did read it at one point. There are lots of volunteering opportunities at PyCon. And I mean, this is a community-run conference. It really helps if people volunteer. And they asked me to give a pitch for if you have spare time at all, go volunteer, stuff bags, work the registration desk, do things for them. There's some highlights. Oh, I just copied and pasted. He told me to. There are 3 slides there that you can include in your presentation. So you might go look there. Also, we have a survey available which you can take for your feedback. Your feedback is very important to us. We need feedback so that we know what to prepare next year and things like that. So I'll get back to you after the tutorial or after the break on exactly where that is. I didn't get that link up. All right. So what are we going to talk about today? So today, I'm going to talk about hardware, something that you're probably not going to hear very much about at PyCon, but I think about a lot because I work on supercomputers. And the first thing I want to kind of go through is what is happening in hardware. Why does it affect you, and what is it going to do? Let me be kind of blunt or honest here. if today, everything you learn today, I would be surprised if you go back home and like make use of it exactly now, right? If you're doing something that's very HPC intensive or something like that, then you probably can. Or if you have something, if you want to process 10,000 images, or if you want to, run a password cracker or things like that, definitely going to give you things that are doable today. I see someone laughing. Don't laugh. Security guys should do this. You should run password crackers on your guys to protect your users. But I also say coming architectures. So everything I want to talk about today, everybody in the field thinks is going to be standard in 5 years. So while what I talked about today and the issues I talked about today may not be exactly affecting what you see today, it will be something you should know about and you'll see more about things and how it's affecting what's going on. And so that's kind of my real motivation for coming here and teaching this sort of thing, but also get people, because I think doing some performance stuff sometimes is fun. And then my outline, I base of kind of vectorization. How many people know what vectorization is? Okay, so some of you guys, that's good. Some of you guys pay attention in your CS classes, that's good. We'll talk about some parallel instructions, and then I want to talk about the CUDA and OpenCL languages. I use these things interchangeably because I use them all the time. But they're a little bit different. CUDA is a proprietary language from NVIDIA, and OpenCL is kind of the open standard that's been kind of ratified and supported by Apple and Blizzard and lots of other people and Intel. So you can kind of think of it as NVIDIA versus everybody else. The truth of it is that NVIDIA is really winning this war, and that CUDA is like really nice to use if you're like want to just get started and an honest kind of person. But OpenCL, I think, is the way to go for the future. But it's kind of like the DirectX versus OpenGL thing. I mean, that still goes on, right? I'm going to give a little bit of a survey of some of the Python projects, and then I'm going to try to do a hands-on demonstration, and that's going to be the bulk of the last half. So the first half, the first 90 minutes, I want to go through these 5, and the last half, I just want to give an interactive kind of like go and do it. Okay, so that's the idea. And feel free to stop me, ask me questions. I'm totally not offended. If we don't get through all the material, that's fine. This is about you guys learning, not about me giving you everything I know. So definitely feel free to do that. All right, so we're going to talk about hardware. So how many people know what Moore's Law is? Okay, most people in the room. Everyone knows that Moore's Law, you have a doubling of your transistors every 18 months, makes your code go faster, right? Wrong. Your doubles the transistors, but that doesn't double your code performance anymore, because your code, a serial code, is dictated by what? Your clock frequency. All right? Yeah, I heard some people say that. So now what's happening is we're still getting doubling the transistors, but what do we have to do to actually utilize all those transistors? Parallelize. Parallelize, hyperthread, use special operations. There's a whole bag of tricks. Now the next trick out there is massively parallel machines. And I'm talking the thing where you have 1,000 threads on a core, right? So your GPU already does it. There are CPU things that are coming out that do this sort of thing. It's been in gaming devices for a long time. But now that's kind of coming out. And this was kind of seen a long time ago by GPUs, and here's a graph, and I'm sorry if this cyan color isn't coming out super well, but you see what happens is that you have here your theoretical flops, and once you start doing lots of parallelism, you see a real takeoff in the number of flops, floating point operations per second. And these are actual NVIDIA chips that started taking off in 2003. Now, this cyan curve is the GPUs, and these blue curves down here are your traditional Intel beefy Xeon class server CPUs, right? So you notice that there's a huge disjunct between what a CPU can do if you use it right and what a GPU does. So we have a lot more transistors, but we're not using them. And we have to change our model of computing to do that. Another kind of point here is that for a scientific computing guy, for a long time you didn't have any Oh, can you see that blue? Oh, goodness. Kind of. It says 0 double precision. So what they started to do is they have to take out certain things in order to make these achievable flops. For example, they only use single precision numbers. Okay, so if you're somebody who doesn't ever use floating point precision, you probably don't care. But if you're somebody who really does care about that stuff, it kind of goes back and forth. And so that's why you have this Tesla line, which is, I guess, a black line, here that shows where they started to care about actually speeding up double precision. So just because you have more transistors doesn't mean you have more actual performance. So what changes? What changes to get that performance out of your chips? So a GPU, well, a CPU and a GPU, the biggest, most aggressive change everybody notices is there's just a difference in the number of cores. And those cores are different types of cores, but it is the case that on a CPU, I think you can get up to 24 cores today or something like that. And a GPU, you kind of start at, depending on how you count, between 32, 256 to 10, well, I think there's a 248 now. So right off the bat, you get a lot more cores. But the second line is really important, is the complexity of those cores. So if you, in your CS architecture class, you learn about a pipeline. This is how you pipe instructions through your architecture. So the Pentiums really went out on the deep end to make serial code as fast as possible. And for many years, they kind of took this line, we're going to make serial code work super fast. And we're going to do things like out-of-order processing. That means that they actually change the order of your commands. They do really fancy branch prediction. And they have lots of stages. And so that kind of affected code in many ways, but that kind of day is kind of done. And the reason it's done, I should have put this in the slide, is this thing called Amdahl's law, which is going to take over Moore's law in the next generations of architectures. Amdahl's law is a relation with the amount of power it takes to do an operation and a coefficient that's unitless. And the thing that Amdahl showed is that producing flops is inverse to this coefficient. So for every flop, my coefficient, I can produce a lot more flops and not have this coefficient go up. So my power doesn't really go up that much. But when I move words, when I actually move things around, so I take something from my memory and put it into my architecture, it's linear. So it costs me, today, it costs about 50 times as much power to move a word than it does to compute a word. Okay, so if there's anything we're seeing actually happen from your cell phone to your computer to your TV, everywhere, power is the budget everyone cares about. And Amdahl's law is how we design our algorithms in order to make sure that we can hit a power budget. So those are more or less the major characteristics. I always like looking at what hardware kind of looks like to give me an idea of what's going on. And so this is the Nehalem, which is an older chip now, but it gives the idea. If you looked at the Westmere or the Sandy Bridge and the Ivy Bridge today, it would be very similar. And what you see is you have some cores, and these are the only things actually computing, right? The cores are the ones that do your multiply adds, move your data around, transform that data. You have a whole bunch of other stuff, your memory controller, your L3 caches, miscellaneous I/O, and all sorts of other stuff where you have to dedicate your transistors to manage feeding these cores in this complex fashion. Here's the Westmere chip that came out. Largely the same story. You can see kind of where the computation is, but a lot of the chip, I mean, it's probably less than 50% of the chip is actually used for computation. Here's what a GPU looked like, and this is an older GPU. But what happened here is that you had a lot of cores, but your cores are actually split up to the four processors. And another thing that happened is your memory ended up being a lot closer to the cores that are actually using it. Okay, so when you have a graphics pipeline, this was what they kind of came up with. We need to put that texture, so the textures that are going to map to your games have to be the fastest operation in the GPU because they just want to blit images. And so they put that right next to the cores. And then everything else is some memory, but there's not a lot of memory I/O or anything like that going on. It's basically just processors, memory, and a few other types of memory that's farther away. And then the center that kind of does the scheduling. So that was 2007, I think. 2008, this is what happened. They took out even more of that memory. They put a lot more SMs, and so now almost 2/3 of your chip is actually your cores. And they call them SMs, streaming multiprocessor. And so now they have a lot more chips in this big block, a lot more memory that kind of sits in between that everybody can kind of hit and have this global address space, and kind of show you what happens when you actually change your chip around. And this guy pretty much changed the world for GPU computing, or general purpose GPU computing. So what this looks like in a schematic is something like this. I have an L3 cache in the middle, and I have a bunch of engines that have register files inside of them. You have 8 of these, what they call streaming multi-units, but in each one of them there's 32 actual little workers that actually do your actual work. So every time you run a thread, every one of these little boxes represent a thread, these green little boxes. And so there is just kind of like what you kind of look at when you see a GPU. Oh, that's a clear picture. Now let's go in on one of those SMs or kind of scheduling units. So what we have here is you have your instruction cache, your scheduler, but the kind of the neat thing here is you have a register file. So you usually don't think about registers in Python, but in CUDA you can actually map registers very closely. And so one really cool thing for a performance guy is that, hey, I can actually get to every bit of my memory and every bit of like what's going on everywhere in my core, whereas on a CPU that's very difficult to do. And so that's why I've always been super excited about this. Every single core is represented by this little guy here, which is just a dispatch unit. It says dispatch unit, operation collector, a floating point unit, an integer unit, and a result. So it's very bare bones. And that's a schematic, and there's a few other things going on, I'm sure, but that's basically what you can look at. You have a few more things in your, if I showed you a schematic of your CPU, you would have a long pipeline, and this would just be one of those pipes, right? And you'd have a lot more, and it's actually kind of a lot more complicated than that, but I won't go into that. But that's the idea. The other kind of thing to notice is that, I didn't put this on a slide, but it's a lot slower. So your GPU or your CPU runs about 3 gigahertz, and they've kind of tapped out at 3 gigahertz because power. You go much beyond that, it kind of power issues kind of start happening. These guys, they clocked them down, way down, and I think that they run around 1 gigahertz. So it's about 1/3 as much computations per cycle, or per second, right, than your what a CPU could do if it was fully fed. Oh, so here's a lot more of the details. So if you know a lot about hardware, you can think about it this way. Here's the 4 chips I just showed you. The Nehalem and Westmere's, you have basically 4 or 6 functional units. There's actually a debate as what actually is a core in this field, so that's kind of why we use the word functional unit. 30 or 14 in the Tesla, which was that double precision. Oh, both of these are double precisions. Tesla's an older one, Fermi's a much newer one. Now they have a new Kepler that I think Travis might talk about, or at least some of his colleagues are later on. Here's your kind of your speed. You can see how your 3.3 is kind of your top out, but we kind of move back down to 1. So another thing that's really important is what you call single instruction multi-data, but width. So a vector, if I have a vector of objects or a vector of numbers, vectorization largely means doing the same thing on all those things at once. And so these things have been around for a long time. I think in the 80s, this was the way you did computing, was you put together vectors and you you issued instructions that acted on vectors only. And what happens today is they kind of went away from that, but they're actually still there. And if you want real performance, you really need to use them, but they're very hard to use on the Intel chip. So if you really want to use these on the Nehalem and Westmere, you can get a 4x speed up on a flop limited code if you use these SIMT with, but you have to really know how to do it. You have to almost insert assembly level instructions in your code if you really want to make sure it happens, which is kind of like eh. But with CUDA, which came out kind of in 2007, they made these SIMT wits very dynamic and made it a lot easier to get to them. And when we're referring to them, we're actually referring to these whole kind of core here. So they say they treat these guys all as single instruction multi-thread. So there's a thread on each core, which is very similar to how a SIMD instruction works on Intel cores. Okay, very technical. If that flew over your head, don't worry about it. But the big thing the line I like is right below it, is that if you're on a Nehalem chip, or a Westmere, you're seeing on 10 times, up to 10 times as many, and more, I guess 20 times for the Fermi, 10 to 20 times more instruction streams actually issued. Okay, so now that's great, but you stop and say, hey, I'm using Python. Python's good if it gets 5% of my CPU, why do I care? But I think it's good to know what's happening in these setups. Oh, sweet. Thank you very much. All right. So one word of warning. If you go try to get these numbers, you will probably fail, because these guys are masters at marketing, and so one thing we say is they list 936 gigaflops in their literature, but we only calculate with 624 gigaflops. Any of you GPU guys know why? Nobody knows why? Because NVIDIA includes a special function unit, which handles these exceptional instructions, and you can combine a lot of flops all at once. For example, they fuse, multiply, add, where you do a multiply and an add at the same time. You do some transcendental or a root function that does a lot of flops all at once. So one thing to kind of figure out is, even when these guys talk about these huge numbers, you've got to take them with a little bit of a grain of salt. And usually I half them. All these numbers I gave here are measured numbers. For example, bandwidth is actually measured bandwidth. I think the Westmere actually claims 80 gigaflops or gigabytes per second. But if you just write a simple C code, this is what you can actually obtain, right? So there's always a difference in hardware between what's attainable, what a assembly code programmer kind of measures, and what a real programmer measures. So just so you kind of know that caveat. All right. So that's kind of my hardware overview. And I could go into a lot more detail, but I figured that this audience was probably not ready for that. But I wanted to give a little bit of a history as to why these things exist the way they are. And largely GPU is graphics processing unit, and they were designed to do graphics. The nice thing about graphics is that it is highly parallel to begin with, right? You have pixels on your screen, and none of them really depend upon the others. I mean, they kind of do in the back end sometimes, but they don't always have to. And so a GPU is designed to accelerate this process of determining color based upon some simulation that's going on, and just rendering a color to that pixel. And so you can think of when you have your so in my class I usually grab a computer and show people. I can't do that here, but you can imagine here where every one of those little boxes coming out of that camera is a single thread, and that's actually how they program it. It's a single thread that in a ray tracer you shoot a ray or something, but typically you blip to that screen. What often happens in real code is you have these textures that you plop onto each other, and there's a very fast way of doing what they call shading. And they actually have these languages called shaders that kind of look like this, and they're just kind of a little code that takes some number and some other thing to spit out, and they just say, give me some dot product. So here we just have, I'm going to grab some, so my text sample, for example, the actual thing that produces the color. I'm going to put it next to my light. I'm going to do a dot product to get what my light actually says is the right luminescence of that guy, and I'm just going to return it, right? And so that's what these guys write. We call these, so the old days I call these shaders, and we actually wrote code that actually did neat things in these shaders. But it gets compiled into kind of your typical assembly language. And this assembly has, for people watching, this has a really kind of fun things like clamp, which is totally off the risk chart, and it's a CISC land that nobody would ever dream about, but these guys really do optimize these things in that way. So this is, it can happen in parallel on many independent traces, and the question is, how many is many? And so in this case, it was hundreds of thousands. You really needed hundreds of thousands of these things to hide those. Now, if you try to launch 100,000 threads on your CPU, what's going to happen? Does anybody know? I saw someone, it's going to go down, right? So today, you try it in Python, C, whatever language you want. Like your operating systems just can't handle this many threads typically, because the way threads get allocated, things like that. And so these are actually special threads. They're in hardware, and they really are designed to be used as lightly as possible. Think of a single instruction type thread. And so you kind of have to think about it in that way. So if you do 100,000 gigahertz, so you use multiple cores, and that was the kind of the idea. So they have this work fragment, they have some unshaded fragment that gets shaded, that's going to hit your screen, and you have a very, very independent workflow. So if I try to do this on a CPU, you would have to fetch, decode, do some branch prediction, schedule it, prefetch, and then finally get down to an execution context. And that execution context would have to hit your cache and things like that. So it's not going to really work very well. So the idea was you must complete these things very fast. So they extended the graphics model. Okay, I'm missing some slides. So they extend this model where you basically take out all these red parts for the GPU way. And you only have that blue part. And so now you get these graphics cards. And here's where you could see the reds and the yellows, kind of the actual ALUs and the caches kind of hitting back and forth. So in this example, you could have 128 threads, so you could actually do these guys hundreds of thousands and only thousands of times, right? So every single one of these guys are going to execute this line of code. What's going to happen when you branch? So this is a problem. If I have branch prediction is a huge kind of thing in your computer. Like if you have any decision problem, you really don't want your branches to be broken. Just like we don't want our guild to be broken in Python, we don't want our branches to be broken in other code, right? So what actually happens here is GPUs would just mask off the result. So it would compute the whole result. And you notice I have different lanes here that have trues and falses. And the lanes that have trues are actually used in this, for example, REFL is the code here. And then everybody would compute the other option and mask off the bad result. And so what happens on these guys is you get twice as long to compute this guy. Normally on a CPU, you would only compute one of these guys and you would stop at the blue because the line between the green and the blue, because that's where your data race happens. But on a GPU, you actually have to add your ifs and else together. So that's a big caveat. Everybody asks me, can I get GPU code to working? Yes. Can you make GPU code faster? That depends, right? So if you have very branchy code that doesn't have lots of independent things that don't have data depending upon each other, it's a challenge to get this to work efficiently. But things are moving on. People are figuring out how to change their algorithms and understand that sort of problem. All right, so so this is kind of the same thing I just kind of said, but what happens when you have stalls? So naturally when you have a thread, sometimes it has to stall to wait on something else. For example, a pipeline dependency. It has to wait for data coming out of another pipeline. On your CPU, often you might have to wait on your adder unit to be free so you can use it late after the other adder unit. Well, adder probably wouldn't happen, but definitely for division or sign functions or things like that. You also have memory latency issues, which are kind of, when we say your bottleneck is memory, often you're stalling because of your memory. And this is, if you're a Python person, you have this a lot, you should use gevent. If you haven't seen that library, it does amazing things for Python speed-ups. All right. So we omitted this complex CPU hardware to handle those stalls, but what do we do instead? Since we have lots of threads and we can interleave the execution, we have to really think about how to interleave that execution. And to show you kind of what that means, suppose I have 32 threads, and they all have a data dependency upon the other 32, for example. So typically what you would have in a CPU would just schedule these things correctly. But since we're using a language where you actually tell every thread what to do, you will compute with your 1 to 8 threads, and then you expect a stall to happen, but you schedule the next 8 threads. And this is kind of, you have to block your memory or your algorithms to these, what they call warps in the GPU land. And so these warps you can stall at the warp lines and do as much work in those chunks, and then you actually achieve a lot more multi-threading. So if you do have processes that have some dependencies upon them, it doesn't have to be as independent as your screen is. It can be as independent as, I'm only going to do things in these blocks. And so now you actually do get lots of threading because now you still have execution throughout this slide. So if my x-axis here is time. I do have extra latency because you do have to schedule these things. You have to change out contexts and you have to do things like that. But it's there if you want to. So the cost of multi-threading, you can think of you adding latency to individual threads. You also have more storage. And what they've done is that they have a scratch space, if you will, where you have, I guess it's 8, well no, it's 16 or 32 depending on your GPU. But your storage pool is a little piece of space that all those 16 or 32 processes can access very fast. So in order to alleviate those data dependencies, we put some scratch space in there that you can actually control inside your code. And everybody can access those guys. So your big memory, so when you go to a shared memory, so you add a whole bunch of these guys and you have a shared memory where you kind of store your bigger files. And these storage pools are really small. And when I see really small, I mean like thousands of kilobytes. So it's kind of one of those things that if you have something that fits in the thousands of kilobytes range, you can really access that very fast. But if you have to go back to shared memory for every single operation, your memory is going to have some problems. And we're going to talk about memory systems here in an example in just a minute. All right, so here's an example system. So if you do all the numbers, you scale this guy out and put everything together, you get a teraflop at a gigahertz. And this is what the big kind of number that people, in 1995, this was the biggest computer out there was a teraflop. And now it's in everybody's laptop. Okay, so that's kind of the milestone there. Here's the GeForce, which 16 cores, 32 SIMD functional units, and something I didn't really talk about, you have 2 warp schedulers and 2 instruction dispatch units, so you can be scheduling two different contexts at the same time and have 2 different things going on. So you have thousands of threads, but you can only have 2 programs running, basically, is the idea. So here's an AMD version, and we explicitly, so they have 16 cores per floating point unit, and so sometimes the lingo gets different from different vendor, and you can really see kind of some fights between the vendors here. So AMD calls stream cores, and they're called streaming multiprocessors on NVIDIA hardware. Okay, and they have the same sort of concurrent threads. They call it a wavefront, but that's fine. All right. All right, so here's another example, and this is where it gets really interesting in my view. So everything we've talked about before was a GPU. It used different assembly instructions than everything you've ever used before, or normally programmed. This card here is the same idea, except it's an x86 core. And it's called the Intel Mic, the Mini Integrated Core. And they've had quite a few of these things, a line of these kinds of things out in the development for many years. I think there's a thing called the Larrabee. How many of you guys heard about the Larrabee? Okay, so some people are on top of this stuff, right? So then they have a thing called the SSC, and now they have what they call the Intel Mic. That's the architecture class, but the actual product is called the Xeon Phi. So if you ever see a Xeon Phi out there in the wild, you can basically think of it as a GPU that uses x86 threads. More or less. There's a lot more details, and they kind of use some of the same kind of techniques that they use to get parallelism out of the Ivy Bridge and Sandy Bridge processors, but they're doing the same sort of thing. They've moved to an in-order CPU. It's a lower clock frequency. It's 1 or 1.1 gigahertz. And they have a bunch of them on here. And it's basically kind of a new thing that people are trying, but it's a first-generation product. And so people often ask me, if I run code, will it work on the mic? Yes, I've gotten code to work on the mic. I've gotten Python to work on the mic. But right now, it's pretty darn slow because this product came out January, basically. And so this is really hot product, and you probably can't even buy them unless you buy on the order of like 1,000 at a time kind of thing right now. And I just kind of put it in here because it's the nice kind of new cool thing, and it's what I look at being, you know, this is the indication that this is our future, right? So we're going to be seeing this a lot, and I know that Python community is thinking a lot about how do we thread things, and here is a working box that actually is out there in the wild that will be probably the evolution of our Xeon cards in the future. All right. Yeah. So the question was, isn't Ranger all mic? And to give context, so he's asking about a machine at TAC, but Stampede is what you mean. So to give, at the Supercomputing Center, we have deployed, I wasn't going to talk about it too much, but we've deployed these cards on the order of 6,000 of them. And so if you are a scientist who is part of the NSF and you want to play with one of these, talk to me afterwards and I can get you on it. If you're a company and you want to pay money to TAC, you can get on it. But I'll send you to the business person. But yeah, so we've installed 6,000 of those. But they are only 2 petaflops. Or no, okay. We have a 10 petaflop machine. 2 of those are this Ivy Bridge or Sandy Bridge cores. 8 petaflops are these guys. But for all intents and purposes, these are the experimental units. Our scientists don't use these nearly as much as the other side. So, great. So here's, just so you kind of have it in your slide deck, here's some terminology that kind of changes. So getting back to the name changes, so x86 will call it a core, NVIDIA will call it an SM, AMD will call it a SIMD engine. And so you see how they have different names, but the SIMD lane actually, what a vector lane in x86 core is more like a CUDA core and a stream core and things like that. So that's just wanted to give you a slide on kind of the graphics. All right. So that's kind of a look at real systems and how they happened. I want to give some time to talk about the memory system, and I guess we have a good amount of time. So while the threading is important, understanding like we're doing a lot of threads and they have to be put into blocks and they actually map to slower cores, but memory becomes another thing that's super important. And the memory model changes quite a bit. And this is in computer architecture, there's a huge fight about how we're going to do memory in the big cores. For all intents and purposes, the memory takes up a lot of your power in your GPU or in your regular CPU and other chips. And so memory is a big kind of an interesting thing that's happening these days. And I'm just going to go through kind of what the tiering of your memory looks like when you have control of it. On your CPU, everything gets controlled. You never have to touch it. And sometimes that frustrates me, but it doesn't frustrate everyone. But for a GPU, you're actually able to really control your your memory. So CPU, we have multiple levels of cache. You have your L1, L2, L3 cache. And the idea is you take care of local temporality. You know, you bring in a whole cache line, and the idea if you want fast code, you use that whole cache line instead of only one element of that cache line. Today, it's true that if you're doing computing and you're not actually putting your accesses to your memory in order, you're getting basically a fourth of the bandwidth that you could possibly get out of your algorithm, and that's just off of caches. So we have a controller there. That aspect that you really can't control your CPU levels of cache is a big deal in optimizing your typical cores. Another kind of interesting fact here is that you have 25 gigabytes per second to main memory, and this is per channel socket, so you can actually get more. I think on the Ivy Bridge they've kind of pushed that to, you have 4 sockets, you can get to 100 gigabytes if you do everything quite right. So that's kind of that's kind of the standard CPU style. But the GPU, like I showed in those pictorial diagrams, you have basically you have 3 kind of levels of the cache. You have your register files, you have that shared space, and you have the scratch space that's shared among the units inside one of those SMs. And then you have a global space on the chip, right? But you also have some other kind of fancy things like the read-only texture. So you can point some memory saying this is read-only memory, so access it fast, right? So for this program's life, you're only going to read only this guy, so we're going to push it through, and we have pinned and things like that. So they say there's no cache hierarchy, but now they're kind of coming back on that because people want caches turned on. I typically don't turn them on because you really have to be able to organize your code in a way and make the compiler do it automatically, but I like to be able to push those bits around myself. And so you don't have to turn on a cache, but if you do turn on a cache, it goes through those levels in a similar fashion to how your CPU goes. But you get much higher bandwidth to main memory. Now, I guess I should make a caveat here. GPUs are connected through a bus. So you have a PCIe bus that controls all the data that comes in and out. So when you talk about your memory on your desktop or your laptop, you say, oh, I have like a terabyte of memory. Well, yeah, and so you have a big terabyte like main memory. Now to actually get that to the GPU, it has to go through a CPU, through a bus, and into the GPU's memory. So when I talk about 150 gigabytes per second, I'm talking about if it's on the GPU card. Now to actually access that terabyte of memory that you bought from Fry's and put in your desktop, that's going to actually be more on the order of, I think it's 2 gigabytes per second. So it's like way down. So you have to kind of mitigate that. So if I move everything to a GPU, I have super fast kernels. But just straight out of the box, if I don't have that, then you're going to have some latency to hide. But in the future, they're really trying to push that away so they get GPUs actually on your socket, so they have access to that main memory much faster. I don't know if you follow the PS4 was just announced, and they have an in-socket GPU on the PS4. If you want to go purchase the next thing that actually has some interesting things. Now, how many people actually program for the PS3 here? Anybody? Okay, we have one guy. I mean, William's done everything, but the cell, yeah. So the cell processor counts, yeah. So I mean, now it's kind of like they've always, the PS3 is the PS stuff has always been like the leading edge, and like things that they did is kind of what the mainstream is starting to do now and things like that. So I think it's interesting that they've chosen this thing that we've seen coming for a long time. So, yeah. Yeah. So the question is that when we programmed for the cell, there was a magic compiler that IBM provided, which William calls the Octo compiler. I didn't know that it had that name. And this was true of the old Cray's machines in the 80s all had a special compiler that took care of all this stuff for you. Today, you have compilers that try to take care of this stuff, but nothing's magical at this point. This is definitely an open. I see domain-specific compilers all the time talking about GPUs and things like that. And when Travis gets up, he's going to talk about his compiler technology, which actually is a Python to GPU kind of compiler. Well, that's one aspect of it. It's more than just that. But so the compiler technology is catching up, so you don't have to worry about it. But it's not quite there. And my view is once a compiler gets it, you can't have the fun. So this is. So before we get into memory, we want to remember that we have this big cache here. We have these little SMs, and they have a shared space right there. So you can kind of think of this guy as your memory spaces. So you have your device, which is this light blue. And it's attached to this host through a PCIe bus. You have local, global, and then there's two that are special. There's constant, which constant and texture. They're both constant, but constant is kind of everybody access this memory, and texture just happens in an allocated fashion. So these 16 will get the other 16, the 16 memory addresses right together. Okay, so those are kind of the different, and the multiprocessors go back and forth between the locals. They have a shared memory on them, and they have registers on them. And the register space is super small. Like we're talking like 8 registers per core, right? So if you really want to optimize these things, understanding register pressure is like the key to like really pumping out every bit of performance of it. You can read my papers on that. You don't have to go through it today. Okay, so that's what these guys look like. That's the same sort of thing. You also have a hierarchy of, okay, so that's what I want to say here. So you have this hierarchy of threads. So you have a single thread on these green guys and blocks of threads. And the same thing here. So you want to actually be able to have per thread what they call as a thread block, sometimes called a work, it's either work group or work item, and a slide later will tell me, but AMD's word I think is work item for a thread block, so a single block of threads, right? So then you have a grid, so is these kinds of blocks, and the thing is you pop up 8 of these guys, and that becomes a warp or a work group. And those work groups act in simultaneously, basically. And there's a per allocation context for each one of these things. So you have to kind of, if you really want to get the last ounce of performance out of these guys, you can think of it in this hierarchy, where we have a thread block. So a thread's going to access my registers and my local memory very well. A thread block can get to have all access to the shared memory, but they can't access each other's threads, or registers. Okay, so you see how we're taking away things you can access as we get down. When you think about a warp, you can't think about the whole warp accessing the shared memory because they're split, right? So one work item or one thread block has different memory from another work item or thread block. Okay, so now you've split your memory space. And so this looks a lot like distributed computing. And so if you ever work in a distributed world, I mean, so Hadoop world, right, they think about way down here, you can think of this as being your single, I forgot the Hadoop word for the single runner, the function space, right? And this is kind of the shard on node. And different shards can't really talk to each other very well, at least in the mainline idea. So, I mean, it really comes back to this old distributed computing ideas there. Okay. And I'm terrible at these talks because I never pass it out that way. So this is kind of the lines of what I just said. Okay, so you have to know how, so when you have different memory hierarchies and you want to know these guys, you also have to think about their lifetime, right? So my register, and so what we call local or register or local, depending on which programming language you use, you get one thread, and if it's local, it'll stay with that thread when you run it again, whereas registers only happen per kind of warp allocation. So then you have the shared, which is have all access in a block. Then global is all threads plus the host, and constant and textures are kind of different takes on global. Okay, so that's the and this is for the compute. So there's different compute capabilities in the NVIDIA world. This is 2.x, which we have on our on the box that I gave you access to. Okay. So that's the hierarchy. You have to remember that when you code. But the next kind of big thing to think about is coalescing. And so the idea is that you have to be able to access memory that's in chunks. So if I have 10 workers, they need to be able to access those 10 items. I think the analogy I really like is Walmart. So Walmart, whenever they pack their store, they put everything on a pallet that they drag through the store, and it's almost automatic. They flip on a switch, and you have workers taking things off those pallets and putting it on the shelves. And so they pre-allocate everything, so when the pallet arrives, it just goes through, and they access right in a row. If you had a worker that had to get something at the bottom of that pallet, it would take them a long time, and it would screw up everything. And that's the same thing about memory coalescing. It just becomes very important on a GPU as opposed to only somewhat important on a CPU. If you actually want performance on your CPU, you have to care about this. But most people worry about that later, right? So it's probably one of the biggest kind of things to worry about today is how do you actually allocate your memory. And to give you kind of some examples, here's we have, for example, a warp of threads. So we have a half warp of threads, which are these bottom white boxes, and we have two or a little bit of memory. One that's the blue line, so every line is 64-bit aligned, meaning that they actually happen on cache lines, and that you know how to access the data. Because the way the architecture works is you align data on actual, I forgot the word now, but you align it so that you can access it into the TLB and other things very quickly. And so this is what we mean by aligned. And so, for example, if you have 64 bits aligned and 128 bits for the whole thing, bytes, no, bits, right. So it should be bits, but it's, yeah, we can go with bytes. It doesn't matter too much there. It matters for the actual instruction, but for this lecture it doesn't. So I'd have to go look at what their specification really says. So if I have so all the slides use bytes, but I think that's wrong. I think you actually have a 64-bit instructions. So if I have 64-byte transaction on an Intel Fermi, that means that on one of those cache lines, I just get every single one. It's aligned, every single thing happens, right? Now what happens if I offset? So I'll show you some numbers. So an offset is when you're not exactly on the line. So you've actually moved off and you're getting things in the next line. So the 65th to the 129th bit instead of the 64th to the 128th bit. And then you also have boundaries on off your 128 byte. And so all of these guys end up being so I guess the boxes here is when I just have them all in line in a cache, I only have to pull in that box, which is only 64-bit. But here I have to pull in two lines. And so I actually pull in twice as much data to get those lines. And then if I'm on a cache line and your architecture supports it, I can get in a half line. And this is quite common. So I'm off of this register, but I'm 128 aligned, so I can still get this guy there and only get half the word in. Okay, so what does this do to your performance? Okay, so these are two GPU cards, and the top line here shows you what happens with the offsets. So you get 120 gigabytes on this GTX 280, which is There's so many cards anymore that I forget what they all are, but that's the name, right? I think that's the probably a Tesla chip. And so you get 128 gigabytes per second, but the second you go off, and you jump to half. And you stay at half, and you have a little blip in the middle, but you have not much later until you get to the next word. So if you're trying to optimize and do memory operations, you really have to worry about how do I align my memory. And so thank God Python lets us use C, and we can actually do this. I don't know if NumPy actually aligns things. No? Okay, well. 12, what do you mean, lower? Oh, here it is, but you know, when you have these measured numbers, I'm surprised it's as flat as it is. Often there's like little wiggles, so that's in the noise, right? But this one is a real bump, and that one's the half switch, right? So I don't know why the plot produced 12, a little off, but all right. So that gives you an idea. And on a GPU, the model is you have a half warp that accesses. So you have 32 threads in a warp. Half of them need to be accessing either the same thing or things very close to each other. Okay. Okay, these are the same slides. Why am I? So, okay. That's it. So another thing you can do is strided access with a regular pattern, and NumPy does do this correctly. And where you really do you want to be getting memory, but it's kind of spread apart. At least you can get only twice as much memory when you stride, and you can coalesce in that guy. And so if you stride, you can see how the strides actually affect these guys. So if I do just a single stride, I actually only get double, but at some point it doesn't matter anymore because my stride becomes too far apart. So, and this is actually an architecture kind of call if you really want to do striding. Okay, so yeah, we ask our students, why does this curve flatten out? I won't put everyone on the spot, but more or less it flattens out because you've kind of hit your bandwidth limit anyways. So you can only pull in so much, and so now you're just streaming through that bandwidth limit. And so whether you're asking for 20 or you're asking for 5, well, there's a latency to that anyways. So, all right, so now I'm going to show you a little what this looks like in C, and we'll get to the Python stuff later. So here's an example of just the aligned sequential copy, which you end up saying. So in CUDA, you say global like this. In OpenCL, we say global without the back under, but that's okay. So we call this, so all this guy means is I can call this code from my host, right? So the CPU can call this host, or the device, like the host. I use the word host and device a lot. When I talk about OpenCL, you can actually treat your CPU as a device in OpenCL. And so this is something that's kind of fun to do in Python, because all of a sudden you can use all 12 cores you have with OpenCL and kind of with a short amount of code. And later that's what I want to kind of show you guys how to do. But so from your host, so you have a global space, means I can call this guy from my host and it will run on the device. In CUDA we say blockdim.x, so this is how I index into those number of blocks. So I showed you we had a number of blocks, and in each blocks you had a thread ID, which was your block IDX. So in OpenCL we say blockdim, or CUDA we say blockdim, in OpenCL we say global ID, and in we say block ID X for the actual thread inside one of those groups. Okay, it's .x, and so okay, it's here we're doing block X times block ID X because it is a grid. And they map it to a 2D grid because they're mapping it to your screen, and that's kind of how they think. In later compute devices, you can do a 3D grid, but early compute devices didn't support 3D decomposition. So if you want the absolute address of this guy and you did a 2D grid, you would say, well, let me index into that by of taking the number, my thread ID X, and multiply it through the block ID so I know how many to go forward. And then that's the one that actually picks out the actual indice. And so you would just go and say my out index equals in index. And that pulls that in from wherever you were saying you're copying data from. And so when I write, so this is, I guess this is my first example of a kernel. And so this is a very simple kernel that gets called by every thread. So the idea being, when I call this guy, I'll call it with special syntax, and I'll say, for example, I want 32 threads and like 32 blocks. And this will set up all the data I need to know, and every single thread will run this guy in its context. So that's kind of what we mean when we say kernel. We mean a small snippet of code like this. Okay. I love you, PowerPoint. All right. Here's the example that we did with the offset. All we did was add an offset to it just to show you how you test this code. And that does the offset there. And there is, so how you set up your memory, I guess the thing that's not being showed here is that in order to get things aligned, you actually have to create your buffers. And when you create a buffer, there's syntax for doing that, for actually aligning. So there's our offsets. And here's an example of a stride. And so the same sort of kernel, except you're going to multiply by a stride. And so if you think about how NumPy works, this is basically all it does under the hood, is it stores its memory in a big long line and then uses these kind of offset type things to access it. So, all right. It's a lot of details about memory, but here's a few summations. Each thread has its own set of unique registers. There are people who actually program these registers like very carefully. When you get started in GPU programming, I suggest not worrying about them and just getting used to the paradigm of thousands of threads. But if you really want to get the fastest performance, the register is the fastest memory, and the more stuff you can put in your register, the higher bandwidth you will have to it. When you have too many registers, it spills to local memory. So if you have register pressure, it'll actually kind of try to take care of it. So there are tools to tell you how much registers are being split and things like that. But just so you know that it won't die if you use everything, but it will slow down quite a bit. So so this is the split out in PTX is the assembly language used by NVIDIA, and that's what you can kind of see where .local is used inside their assembly code. So local is memory, it's actually in its global memory. So it's its own space, so it spits it out into this global memory, and now it's super slow, but it's its own access space and it's coherent and things like that. So you have kind of long latency. That's kind of registers in a nutshell. Thread blocks in shared, all threads access thread blocks in shared memory. And so really what often you will do is if you have code that you can't access in that coalesced fashion, the idea is load that memory, coalesce the memory, copy it into your shared memory, and then you can actually access it very faster. Okay, so while the pulling memory from global stuff seems very restrictive, well, you have a little bit of that scratch space to kind of do access back and forth, and that's where the data independence can kind of go back and forth. So I showed you very at the beginning how do you get rid of the stalls where you do it in blocks, and those blocks you store the memory into the shared space, and then you have that access. Yeah, usually what you'll see in fast kernels is there'll be a copy from your global memory to your shared space, and then some operations on that, and then a copy back from your shared memory to your global space, keeping in mind how context switches work and things like that. All right. Global memory, accessible to all threads, but it's, okay, so, yeah, this is badly worded, but it's not resident on any single SM, and it's the slowest memory to access. So global memory is basically about 8 to 16 gigs on your typical GPU, and that's what's located on the disk, and you load that from your CPU to there. So your CPU can't access anything but the global memory. Okay, so now early chips, you would have problems that if you need more than 8 gigs, how do I deal with that? Well, today you can have, there's ways to make that spill out into your main memory, and then you can have a kernel that all of a sudden gets really slow but doesn't die. Okay, so that's just something to remember. If you want to, what they call pinning memory, you pin some of the memory and it pulls in what it needs and puts it back as it needs it. So there's a 64K of constant memories. So I didn't talk about this in too much detail, but a constant memory is can be as fast as a register read if every SM actually accesses it. So if I have if I have like 10 parameters to my functions that are all the same for every function, you would just store that in the constant memory so that I don't have to worry about it, and then just pull it down from the SMs, because even when I call my functions, that memory has to go somewhere, and that ends up usually going into your local space. Using constant memory is how you usually pass those constants that you read a lot of from different files and stuff like that. But you can use it for other things too. So. And then also you have textured memories, which I don't know if we're actually going to cover it here, but you provides 6 to 8 K of cache per SM, and you get a whole bunch of these, 128 megabytes for, okay, so you get 8 to 6 cache per textured memory, but you get 128 megabytes for the card. And so you can actually have a lot of textures. And the idea goes back to the graphics card. So if you have a lot of things that you're just going to read an array in, right? You're going to do some correlation matrix, or you're going to do something on an image that you just read and you write the result somewhere else. You use textures for that. And so that's kind of a very nice feature. All right. So let me go ahead and expand this guy all the way up. So what are the implications of GPU bandwidth based upon these this memory hierarchy? So you have a wide bus, and with DRAM organization, you can schedule your memories to be using the most efficient bandwidth possible using this hierarchy, guys. What it means is that if you have a peak of 14 gigaflops, and your memory bandwidth is 150 gigaflops, you must have 7 flops per byte to actually use your full bandwidth, or else you're bandwidth limited. Okay, so if you're just doing something very simple like calculating something times something, or an average of a couple of numbers, you're going to be bandwidth limited. You're never going to reach that 150 gigabytes. To give an example, I think on the I know the number on the AMD Barcelona, but I think the number on, so you can get the number up into the 50s needing flops per byte on your Intel chips if you actually, since it's such a much lower clock speed and much lower gigabytes, or higher clock speed, gigabytes per second is lower. So you end up needing about 50 flops per byte in order to get actual full saturated of your bandwidth on a CPU. Okay, I said that incorrectly. So your bandwidth here, so if I have 7 flops per byte, that means that I'm going to limit I'm going to hit how much I can actually compute per word I get in. On a Xeon chip, I have to get about 50 flops per byte to actually go beyond my bandwidth limit as far as that goes. All right. So another system out there is proposed the Jalapeno system. So the Jalapeno system, you can get 16 flops per byte at 128 gigabytes per second for your memory flops. And this just comes down from the same sort of numbers. They have 2 teraflop single precision and 128 gigabytes per second. So that's but there's a back and forth because AMD has a better memory bandwidth of flops, so you can get a lot more flops out of your bandwidth, but at the same time it means that the double peak of flops of NVIDIA is double that, or NVIDIA's half of AMD's. So you can get a lot faster on the AMD chips if you're doing a lot of double precision numbers. And that's generally what I've heard from a lot of people I work with. They like AMD chips, but at the end of the day, it's still much better than you can get on your CPU, so they're typically happy if you work. All right. So that's kind of the framing of the memory, the different memory hierarchies, and how kind of all that kind of works. So I guess the last section, and I might just skip through this, or, well, I guess I might just go over and after the break talk about some of the different Python solutions, is kind of how do you program these things? So I've told you about what they are, why they're used. I told you about the threads, told you about the memory, and it's just kind of a different system. I mean, they all kind of a reminiscence of what you see on your CPU, but they're a little bit different. But now you have to change your programming model. And when we talk about programming models, actually Dave Beasley gave a talk at SciPy a few years ago, and he listed out all the models for doing parallel programming. And he had this great quote I love. He's like, you know, the beauty of parallel programming is that nobody knows how to do it, and everyone's trying to make a tool, but really it's more of a state of mind. So it's really about knowing that you're in parallel and knowing that there's a lot more that you have to coordinate when you compute. And so there's a lot of people who are saying, how do we teach this parallelism stuff? Well, for GPUs, they have a completely different model than what you see in your software, your typical software threading model. And so that's what we're going to talk about in this last section, in the kind of theoretical side of things. So the big thing is that the GPU programming is close to the hardware. If you're an architecture person, you want your programming language to be as close to the hardware as possible. If you're a software person, you want it to be abstracted from the hardware as much. I think that the CUDA and OpenCL programming models are enough different that it can help both worlds, but it is the case that we have to go closer to a GPU hardware. That means that we actually have to know that we're going to multi-thread things and that memory lives in different spaces, and being able to control that to get speed out of our code. Your code does need to be modified. There is no magic compiler, no octo compiler out there yet. And sometimes you have to change how your loops actually just work in general. So you change your logic for how do I execute by teams of threads as opposed to just randomly accessing your memory. But the kind of the nice thing is that they've added a few changes in the syntax of the code. So the syntax has a few minor details changed. So it mostly looks like C, and I'll show you some of those guys of today. But there's things like I just showed you the global, for example, and that's a change in the syntax of the code. So you can help the compiler to know what's going on, and so it's not as foreign as looking at a new language, but it is just a small bit of difference. Okay, and that's the. Okay, we're going to go through this one a little bit faster because I think usually when I give this class it goes over several days, but since we're all here, we've gone over the two-tiered hierarchy of grids and blocks, and so when you do on a CPU code to a GPU code, you thread to a specific loop. So an idea would be if I have a loop iteration that's I12 J27. Well, we're going to translate that to thread number 1202. Okay, so instead of a very quick way of getting parallelism out of your code is find that loop that has 10,000 iterations nested in it and just change it to thread IDs. Typically, you want to do very small things in your kernel. So one thread's mapped to a very specific loop iteration. There are some trade-offs between kernel launching and your threads, but that's kind of more advanced than today. And some very smart people at UC Davis are looking at that. But this so we call this a bijection. Okay, so of one thread, one loop iteration to one thread, but we have these two hierarchies, grid 3 and block 3, which is kind of a confusing thing, but that's the XYZ of the grid and XYZ of the block. And typically, most people only use X and Y. I've never seen a kernel that actually used all three on both of those guys. Okay, so this is just the same thing I said with more kind of details, or said again. So the one big thing to note is like all your blocks are configured the same. So if you have code that depends upon the blocks being ordered, you need to separate that out somehow. Okay, so that just like your monitor was all thread, each pixel was a different thread. You can't know exactly where you are, and if you do, you have to put in a synchronization. And you can put those synchronizations in, but it's going to be a big performance hit. So you have a block identifier and a grid identifier, and on CUDA it's thread IDX, on OpenCL get local ID in both sides. The blocks have sizes, so you can know how big they are, so you can actually get the number of threads in the blocks and things like that. So when you index into this. So an example is if I have a block size of 32 and a grid size of 8, I have 256 threads. And so that means that one warp, so 32 threads all run, and I have 8 of them split up. So my first block goes from index 0 to 31, 32 to 36, all the way through what I need. And so you can get your index for the 7th block in the thread just by multiplying these out in kind of a normal kind of fashion that you should have all kind of seen. All right. So here's another example where we ask the same sort of thing. We do this thread number is block ID times block size plus thread IDX. And I realized there was a typo on my previous slide because that should have been block size when I said thread IDX earlier. Okay, I'll have to fix that. So you don't have to use a 2D kind of decomposition. A lot of people will often just say block size of 1 and grids of like 256, and it will still run as if it was one warp every 32. It won't run one per warp. So for today, we're going to just ignore the block size a lot, and we're just going to use 1D dimension arrays so that you don't have to worry about it too much, and it'll do the right thing. So yeah, so this is kind of back to why we use these guys. You can think about cubes instead of just 2D arrays, instead of a linear configuration. And if you're doing this in CUDA, okay, can you guys see this at all? You guys in the back? Oh, I switched it. Can you guys see these blue things? No? Okay, so if you get the slides, all this says is blocks and grid. It's a little bit of a code, and I think that during the break I'll try to change all these code blocks to they're readable. But you use this thread and blocks in order to get how many threads you have. And so if I have threads and blocks, you can see where my block and grid, and I just iterate out, and there's an example of this guy iterating out. So here's another example where I have how many are my warps, and go to the spread blocks. Okay. All right. So those are the thread configurations. How do I launch a kernel? So in this is kind of the biggest change between OpenCL and CUDA. Is in CUDA you launch a kernel by using this chevron syntax, this triple chevron with inside of it these actual thread counts, how many threads you're using these block guys. And so if you see this in code in OpenCL, that means I'm going to launch this kernel, and it has to be a function that's been decorated by that global that we saw earlier. In OpenCL, we just call a function that enqueues it, and we'll see that after the break. Okay, too many slides on that. So to create a kernel, you have the special attribute global, and every thread will execute that code and the same. So here I have this global diagram, and it's just a function declaration that says do this. So if you put global in front of a function declaration, that means a host can call it. If you put kernel in there, do I talk about? So I don't use this in this class, but you also have a special attribute kernel that says only a device can call this. So a device can call a device function if it uses its own modifier. But for this class, we're just doing everything executed from the host. So if I have my chevrons, my grid dimension, block dimension, and it'll set up my XYZ, and you can see kind of a spread of those threads. So we kind of made a big deal about how this guy gets spread out. So if I have 32 by 2 by 1, my block dimension, my grid's 12, 8, 3, you can see that at least my thread IDs, where the IDs kind of sit and how you index them. It's really important to kind of figure these sorts of things out, because this is kind of the detail that really gets people when they're trying to transform their code. Is like, what are my IDs? Because your ID, remember, is that index into your loop. And so we'll show that later when I actually give you some hands-on stuff. Okay. You know what? All right, well, let's... All right, so I'm going to skip over these examples, but they're just showing. So if I have an array from a vector x from x to 256, you can compute this I the same sort of way, and you translate it into. And if you grab the slides, you can see exactly how they translate that out. And so I'll have some work to do to get that back. So we've covered kind of the thread configuration and the loop. But how do we do the data transfer? So that's so that thread configuration and loops. So launching a kernel, we'll get to later. But how does the thread allocation happen, or the data transfer? So there's two kind of there's data that goes from the data to the device by the host and back again. So you actually explicitly have to follow it back and forth. And there's synchronous and asynchronous versions of this guy. Obviously, if you're doing it asynchronously, it means that your execution stops while the data transfers. You can do it asynchronously, where you check and do kind of polling and things like that. And so that's kind of a back and forth, like all the different buttons you can press. So what happens when we pass an array through a parameter list? So the information's, so on a CPU, it's usually stored on your stack or something. And it's in the CPU user space. Well, with a kernel, it's completely different user space. So even when you launch a kernel, your parameters have to be transferred over. Now this is why we often say if you have a lot of parameters, just put them in a constant and transfer them all at once, as opposed to transferring lots of things often. And since so you have to do explicit cooperation. So for example, if an array prime that holds my first 10 prime numbers, I calculate on the host, but I also need to calculate them on the device. So you can either push them there or calculate them there. And so that's often the trade-off. Your host and the two arrays can kind of mean the same thing. And usually what you do is you create, for example, a host and a device. And you make sure that they kind of correspond to each other back and forth through these copies. And I think I have an example. And so this is often often people in code will they'll do something, a mnemonic like D underscore array, H underscore array, or something like that. So there you have an idea of your prime in device and prime on your host. As you develop more codes with this, you develop a concept of like dirty bits and things like this. So the idea being that if I compute something on my CPU, I need to set a bit that tells me that, hey, H prime in this case is dirty, and I'm going to have to push it over before I call a kernel on it, and vice versa. If I call the kernel, it manages it. And so this is a very common thing to do. And so often you can hide latency by only keeping certain dirty things on your device and pull it back when you need it. And so that's kind of a nice trick that you can use by keeping two arrays there. So allocation is done on the host for the data on the host memory and for the device memory. So you can't see this in the slides here, but if you look at the slides, when you download the slides, there's basically a CUDA malloc call. Just like when you, on a CPU, you allocate on a CPU, there's a specific malloc for your device. And in CUDA, it's called CUDA malloc, and we'll see it later in GPU. Then you transfer, just doing a mem copy, which has more or less your destination, your destination, your source, how many bytes, and the flags. And the flags are things like, first there's host to device, there's asynchronous, there's pin it, there's move it to constant, and all these sorts of things. So everything I kind of talked about in the different constant space, you kind of manage through these flags to your mem copy. And so for the most part, for the most part, it's pretty similar to how you would do a C thing, except instead of calling a mem copy, you would call CUDA mem copy, or you would enqueue a data transfer in OpenCL. So your CUDA mem copy is synchronous, meaning it's executed in line and it waits for that to complete before it goes to the next line. But the kernel launch is actually asynchronous. And so you have to either poll or do something to figure out when your kernel is being launched. So this idea being, like, I can just launch kernels and my device can take off and I don't have to worry about it, and my serial code can continue to work. Okay, so that's the main kind of thrust there. But what it does is it means that you have to think about asynchronicity when you run your code, and there are calls to wait, to serialize it to wait, but often it also gives you an opportunity to hide some of that latency and compute something on the device. So the normal code is do something here, execute it line by line, kernel is launched and handed back, so you do something else, and then you just poll until you're done. Okay. So the one thing that this kills is your timers. So if you actually want to time your code, which we're not really going to do today, but you really have to kind of actually put synchronicity into your timer. So a lot of times if you're actually doing CPU code and the timers are just awesome, you might check and say, hey, is my kernel done yet? And so that's a kind of a back and forth. Okay, so let me just speed through a couple of slides and then we'll go to a break. So what's missing? So we talked about here kind of how you copy the data, the thread configuration, kernel launch. So it's just small little things that kind of change the whole mindset, but you have to remember, map out your iterations and things like that. There's data copying for scalars, so you can, when you actually pass scalars, it'll be done automatically through the pass by value, which is the default in C. So it doesn't really hurt you until you have a lot of data that happens that way. So you have to kind of beware of that. The other kind of thing, well, I put here, beware of reductions. So if you ever have to compute a whole lot of things and you take an array and you produce one number back, for example, I just want to know the max of an array. That's, I have a whole lot of data, I just get one data back. And that's one of those things where your parallelism really kind of scales down. But you can also pass it back as a scalar in C, and it gets passed back. I'm just going to skip that one. Every rules and regulations, every device has kind of how many blocks it can have, how many grids it can have, in all these sorts of details, and you can query the device. I have an example of an NVIDIA device that we've queried to show, but you can kind of look at that later. And so that's kind of more or less the gist of things. You change your kernels, you change your memory, you change and you call your functions and make sure that the loop iterations are correct. And you've pretty much achieved kind of what you have to do to code on these GPU machines. So that concludes my, I guess, the theory, or what you want to call it, before the break. So now we'll take a 20-minute break. I'm 2 minutes over, so let's convene back at, I guess, 1:12, or 3:12. All right, thank you. So if you have your accounts and you're having problems, let us know. Right now, my plan is just to give you another account since we have a few more. To fulfill our wonderful organizers' plea for announcements, there's two things that we wanted to remind you of. We have a survey, and I better look at, so we go till 4:40, is that right? Or 90 minutes from now? Yeah. They're about 4:40. There's a survey at this Google PVHDC, which takes you to this lovely PyCon SurveyMonkey site, which you probably can't read, but okay. No, that's not going to help. So, survey, please take it. They really need feedback for everything we do. Another thing, volunteers. They still need volunteers, and they talked to me last. So there's the volunteers. Okay. So welcome back. I see we didn't lose everybody, so I'm not as boring as I think I am. This session, I'm going to try to finish up with talking about kind of more Python stuff. After all, this was about Python on GPUs, and we haven't even touched Python yet. But I hope you have kind of a nice overview of what the architectures are and how they work and things like that. And so now we're going to go, I'm going to talk a little bit about some Python implementations, and then we'll go through an example of PyOpenCL. And I like PyOpenCL because it can run on your laptop on your CPU if you don't have a GPU. And I have a little application I can show that has the Mandelbrot, right? So you can wrap it up in Pygame and things like that. So there's like little codes that you can really speed up and kind of use in your day-to-day life. But right now there's four. There's probably more, but there's four that I'm pretty familiar with as far as Python on GPUs are concerned, and they're listed here. The first one's Numba. Something's happening with my slides because it's cutting me off. It wasn't cutting off earlier, was it? I need to change the resolution. Yeah, it looks like well, I'll tell you what, I'll do both. I will check my resolution, which is the right resolution, right? 640 or 7? Yeah, so there we go. That one? Okay. I just assumed it was right. Okay. Yeah, that looks better. So Numba is kind of a new kid on the block. It's a NumPy-aware dynamic compiler for Python, and we're going to hear a lot more about it later. But the basic idea is PyPy went from Python to RPython to speed up its code. Numba goes from Python to LLVM code. And it started out as a NumPy compiler, but I think they're extending it to more things. It just kind of creates a wrapper around the bitcode. The nice thing about Numba is that since it goes to LLVM, and LLVM is a compiler, has a lot of generators for lots of other things, it also has a generator for CUDA code. And so by using Numba, you're able to use the same kind of NumPy kind of syntax and just have the Numba product produce GPU code. And it's like every compiler. Your mileage may vary, but it's out there. Oh, go backwards. And here's an example of Numba code. So here where you have a sum 2D, and you automatically just-in-time compile with a little decorator, and you turn your 2D array into something that can actually hit. So this code here is not going to hit a GPU, but very similar code where you say, give me the CU version of that. And Travis is going to talk a lot more about that. So that's a very Pythonic way of hitting the CPU or the GPU. Okay, so I was asked in the break, why do I have to worry about all these details? Why don't I just write a vectorized version of my code and let the vectorized optimizer guy, meaning me, write out the interface? And that's kind of what Numba is doing. So it is kind of the case that you can abstract these things out, and people do that. Theano, I just put a lot of their words straight from their website on here. I like Theano. It was built as kind of a project for, I believe, well, it's machine learning, but neuroscience stuff, and some guys in Canada. But it has a nice tight integration. It has kind of a transparent use of GPUs. Their original idea was you have some devices on your computer, let's just automatically go back and forth between them. And I don't have an example of their code, but they actually dynamically, under the hoods, generate things for you. You give them Python, and you call their functions and things like that, and they kind of go to the fastest unit they can, trying to be smart about switching things back and forth. So Theano is a really cool product. I recommend checking it out. I think they use my symbolic differentiation tool, so I'll give them a shout out. The next one is Copperhead, which is written by Brian Catanzaro of NVIDIA, and it's really more about a data parallel language. So Haskell has data parallel Haskell, Python has Copperhead kind of idea. And there they just wanted a small functional language. It's actually a subset of Python. They're not going for, whereas Numba's eventually goal, I think, is, and Travis, correct me if I'm wrong, but I think that Numba's eventual goal is to consume all of Python, or as much as is possible. I doubt that you will ever get nice exception syntax and things like that, but whereas Copperhead was like, let's create as small a language as possible to be data parallel and then ship out to GPUs and things like that. And so one cool thing there is that they actually have a TBB backend, so they can actually hit both GPUs and mics and other things as well. So I didn't talk a lot about mics, but mics you use software threads instead of hardware threads, and that colors a lot of the discussion differently. But you can use on mics, you can use OpenCL as well, so it is relevant what we said. But anyways, okay. So here's an example of Copperhead. So Copperhead, you import from its statement, kind of like the CU decorator, and you write something that looks a lot like Python. And it does things like here where you say, with places GPU, and you give it a context and say, hey, run this guy on the GPU, and it automatically kind of figures it out, right? And so Brian's been working on this for a long time, and it's worked out pretty well. I think that it's also one of these cool things. But those are kind of the high-level interfaces. And I guess if you don't know by now, I like being able to play with the low-level stuff, and I wanted to kind of give people an experience of dealing with some of that low-level stuff. And so PyOpenCL and PyCUDA are the ones, so PyOpenCL and PyCUDA written by the same guy, Andreas Klockner, and they're kind of basically CUDA and OpenCL with all the boilerplate stuff taken out and exposed to Python. And so if I was going to show you how to program in CUDA, it really does take quite a long time to set up everything, or OpenCL. I mean, I think that a hello world to OpenCL is on the order of 200 lines of code or something. So there's a lot of stuff that kind of happens that you have to get. So, but PyOpenCL is one that gives you kind of the complete API if you want it, but also hides a lot of the details underneath. But so it's closer to the API, which means that we'll be writing our kernels in C, but so you'll write your little like small function in C, right, and then just integrate that into your Python routines. Okay, so that's kind of where I think I wanted to go with this tutorial, and after we go through this PyOpenCL, kind of step through and show you how that works and get you on the code, the machines, Travis will take over and show Numba and Numba Pro. Okay? So does everybody have access to the machine? So you should see something like this. Can you guys read this? Do I need to... Are my colors getting in the way? No? Okay. Guys in the back, you can read? Yes? No? Okay, good. So everyone did an IDEV and got to something that says like C something something something, right? Okay? So that's Now you're on the back-end node and the computes, and we can fire off IPython. And so it reads us, oh, I've got the wrong one loaded. Yes. So you guys should see Anaconda there. But since I'm not using your accounts, all right, I think that should do everything. So if you do which IPython, you should see an Anaconda. You won't see a tilde, you'll see a Terrel in there. But show over to IPython, and you get this nice thing that says, I don't have Kern Magic. Okay, yeah, I didn't install everything. So this is the Anaconda distribution, and it comes with quite a bit of stuff, like all these distributions do. And so I want to just try to run all our code samples from this guy so you guys can kind of interact with it a little bit. All right, so first we have to do our import statements. Okay, this might not work. So import numpy as np, import pi OpenCL as CL. All right. Anybody does that work? Not work for anybody? Ben, we might need your help here. Sorry? So on the machine, so the path was, if you want to, okay, let me. Was this the question, what's the path to the Anaconda bin? That's where you should be able to hit there. Anybody else need help? Raise your hands. We've done pi. Yeah, where am I at? Here we go. Okay? All right, we're golden. If everybody's there, we're doing good. All right, so I think what I'll do here is just try to maximize this guy so I can just copy and paste, since it's not letting me copy and paste it. You guys can see that still well enough? So I can copy and paste this guy. So we just do some random, we're just going to create some random variables. So np random rand, let's do 50,000. Notice I say as np float 32. When you just start working on the GPU, it's pretty important to keep your numbers kind of right. And NumPy will kind of, it handles your numbers however it kind of feels as appropriate sometimes. But you can always do this as type, right? And so just going to float 32 will give us that nice single precision number. Okay. All right, now, whoop, 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 whoop. Okay, so the first thing we need to do is we need to create a context. And the idea of a context is that, the context is kind of telling the device where to actually, it's going to compute on. And if you're using a CPU, your context will be your CPU device and it'll figure it out. So when I run on my laptop, I can use my CPU as the device. The difference, I guess, so with OpenCL, it uses the same model wherever it computes. So it still has the same memory hierarchies and the work groups and things like that. But for PyOpenCL, you can just say CL create some context. And this is pretty nice. So you can create exactly which one you want and things like that. But the really nice aspect of this is that you don't have to worry about it. You don't have to go out and get device IDs and figure out everything else. On this box we're playing on, you can see we have actually 2 devices. So if I say context creates some device, it says, hey, you've got Quadro 220, which is an older Quadro card, but oh well, that's what it is. And you pick one. And you can also set it up and so you don't have to ask, right? And so this is kind of how, it doesn't give me a one for the CPU because the way this was compiled is it was linked to the NVIDIA version of OpenCL. And if it's linked to the Intel version, it would give me the CPU. Yes, question? So are we seeing that a lot? Did you guys type iDev? If you do bang host name, and you see SC like that? Okay. So you have to type iDev. So if you look at your piece of paper, and in the instructions there's
from the bottom line.
Yeah. So let me show you.
It's taking a while now, like a minute.
Yeah. That's why I told you at the beginning to do it.
You kicked me out, but I got back.
So you have to do, if you're on a login node, and I have my, so it might have kicked you out. So if you did, you do it again. Yeah. So your iDev-m with the number of minutes. So that command was to be issued now, or like I guess when I started this session. And so some people might have been kicked out because of 190 minutes. But if I do show queue, some of you guys are getting on. Okay, that's not working for me. All right, so as you guys do that, so there's actually not a GPU on the host, and that's why on the login node, and that's why you'll see that error. Okay. All right, so we created a context. It tells us what device we're going to be running on, and we have to keep that around during our execution. The next thing we have to do is we have to create a queue. And so the queue is, since we're launching kernels asynchronously, when CUDA does it, it figures out how to schedule these things. In OpenCL, you just insert statements into the queue, and the functions and devices that need to take part will use them, filter through the queue. So this is kind of your way of scheduling anything from the host to the device. If you're running on a device, you can actually, I think not in OpenCL, but these days it's able to queue things onto the device, but that's kind of an advanced feature. For kind of older things, you pretty much have to do all your queuing and scheduling from the device, from the host to the device. And so all we do here is we say queue, give me a command queue, and you do have some you can switch it from the different devices, and there's like different properties. You can have more than one queue. So in depending on your device, for example, on these devices where we saw there were 2 instruction units, we actually are able to do 2 commands at the same time. So you would have 2 queues that would go back and forth in the context. For this tutorial, we'll only use 1 queue, but just so you know, you can use more than 1 queue. So we create a queue. Yep. So it has kind of swap space that it handles it with. So typically, if you're going to use your whole memory system, it'll slow down between the space, but usually since you and we're going to do that just now, since you allocate your memory buffers, like in your global memory, if you're trying to use 8 gigs of memory for each one, then it's going to have to pipe that back and forth. So if you're using 2 queues, you should still be using the same global memory. And remember, your global memory is available for each kernel. So the lifetime of that global memory is always available there. And it does take some of that global memory to do context switches. So it will shorten it a little bit, but if you wanted them to have totally different global memories, you have to do passing it back and forth between the memory. So. Yeah, I would say if you're going to do the Walmart analogy, the queue would be like putting things on the yeah, sort of. It doesn't. I mean, it's more the pallet mover than the pallet itself. So that's how I would put it. You know, the analogies don't always go all the way, but the pallet mover. So you could have 2 pallet movers, right? And if you only have 10 workers, they can only do so much, whether they have 2 pallets or not. Depends upon how well you optimize or schedule your code. All right, so guys, the guys who didn't have iDev, are we good to go yet? Good? Okay, awesome. Whoa. Okay, so events. So your events get kind of, everything happens as like an event on this guy. And so your command queue, you can actually put computations, memory options, but they all kind of just happen as events that you enqueue. And anytime you enqueue, you can use this enqueue under, and then the command you're enqueuing, and you give it a queue and separate out events to wait for and things like that. So it can, when you have other events, you can actually schedule them up this way. So if I have 10 things and they're kind of dependent upon each other, I can just put them all in the queue at once, and it'll wait for this guy. If I want to synchronize, for example, when I said we have to do timing, you can use a wait command. And the wait command just does what you would think. It polls the event until it's done, and then we'll continue on. So that's what the queues are used for. Here, let's give an example of memory. So we created those buffers, A and B. Now we have to copy them onto the device. And here's where there's a little bit more code involved, not too much. First thing we do, so we call MF, which is our memory flags, which we can have a lot of different types of things for our memory. And so MF, so CL mem flags, for example, we're doing read only and write only, and there's read write, I guess. And then there's, for example, here's a copy host pointer, and we can see dir MF if we want. But the idea here is what we're going to do is just create a buffer. And a buffer is just, we're going to shove bytes in there. And so we say, here's our context. So that's the device we're going to go to. And here's the host buffer, A. And we're going to copy from the host pointer to A buffer. So now after I issue that command, that gives me like the malloc on the card, right? And so you do the same thing with B, and now we create a destination buffer, which is only the bits. And I think the way this works, typically, since we have copy the host pointer, it actually goes ahead and copies it in PyOpenCL. If we were in C, what we'd have to do is we'd have to say create buffer and then move the buffer back. And I'll show you how at the end of this computation, moving the buffer back where we enqueue it. But this automatically enqueues it because we use that copy host pointer over. And so there's a whole bunch of memory flags you can check out. Alec. There's also the asynchronous transfers, but that's going to be later. All right. So here's a few other things. A few other things you can do with the buffer automatically moves things through, but if you do this through event, you would do PyOpenCL enqueue read write buffer. It's long, C-like, but oh well. But there you have things like your offset. You can actually offset it into the device. You can wait for different events, and you can also say whether it's blocking or asynchronous. Not every device out there can do asynchronous copies, but some of them can, and you can get some things like that. There's also mapping from the host space to the address space, and this PyOpenCL memory map can take care of that for you. Okay. Another kind of important OpenCL kind of concept is an image. And there it's just a 2D, 3D resource that just writes to, I guess, it's just basically a tuple instead of your bytes. And they use this because OpenCL is managed by the same people that manage OpenGL, the Kronos guys. They can share the images back and forth. So this is kind of a common way if you have some OpenGL code. Oh, I didn't mention another code called Slither out there. We should have put that on. It's a Python implementation. But Slither is it's C-L-Y-T-H-E-R. Slither actually does this where it maps the OpenGL and OpenCL space together. But let me show you guys Slither. I feel bad because I didn't. All right, well, I don't feel so bad because this web page is bad. Okay, so here's Slither, and you can check that one out as well. It's another tool that tries to do seamless integration between these things. All right, so that's copying the memory. All right, so here's the fun. Here's a kernel. All this kernel is doing is taking the two programs, the two arrays A and B, and summing them into the array C. Okay. So, and this will happen. So OpenCL kind of is it's not a compiler the same way CUDA works, where you have compiled code. It takes strings, C strings, and the library compiles them. And that's not just a Python thing. That's how OpenCL works. And so even when it compiles these guys, you feed in the strings, and you don't have to put it in line here. You can have a file that opens it and things like that. And that's what I often do, is I put them in my files. But here, since they're going to generate code that's based upon that context, and since it changes per device, they actually have to generate it through this command. And so when I say, so you can actually create a program, but I call .build automatically, and that's going to call the compiler inside OpenCL and play around with it there. So that's what's going on in this program. Let's see if we can copy and paste. Yeah, so you could also do the, if you know cpaste, if you want things to look good. So you paste it in and they do lines. So, sorry, I didn't quite. Yeah, so you can't use paste. Just pound paste won't work unless you did an X forward session forwarding, and I told you not to do that. But cpaste is the one that will work here, and that one you can just do a paste and do the. So yeah, IPython tip for you. No, because it'll just build it twice, right? I mean, so the program will be there. And so now we have our prog. Now the thing we have a lot of things in our prog, but it should have .sum in there. Oh, I guess he does it. So we named that guy sum, and we have where that so we had kernel here. So the OpenCL, you put in kernel instead of global, but it's still the same thing. And you say void, and so this global here, that global guy. So that sum is the name of our program. Global tells us that we're going to get this data from global memory, and you put const in here as well to get const and stuff like that. And so from global memory, we're going to access this buffer A, and we're going to access buffer B and buffer C. And so since we're only doing one-dimensional mapping, we say this get global ID 0. So the 0 is to pick the dimension. So 0, 1, 2. So if I wanted a three-dimensional mapping, I could do that. And then all the work this guy does, right, is he sums one thread, a single thread as one loop ID. So if I would write for I, AI plus BI, instead I write this as one function, okay? And so there's a few things you can do to map with kernels. You can see in the slide. So you have your device code. You can have some other build options and change your devices. And there's a whole bunch of different kind of program names. Change things out if you want. But the way I kind of created it, which is the nice, easy way, is through the CL program and the build option. Okay, so now we get to run this guy. And it's very simple. I tell it which queue I'm dealing with. I tell my shape. So I'm telling shape here because I want to tell it how to run the code, so how to iterate. So this is where we tell how many threads. And so we're saying our shape was 5001 because it was an array, a 1D array of 5000. And so it's saying spawn 5000 threads. And since I have two arguments, you can also, I'm not exactly sure why the none here exists, and I was trying to ping Andreas this morning. But when you have two buffers, you can specify, I guess, multiple indexes in the threading. And then you have your buffers. So so that program, since we had 1, 2, 3 arguments, we have to give it the arguments down here, and that's A, B, and our destination. Okay. No, it's for the threads. It's for the threads context. And since you had two of them, you show two. And when I show an example later on that, somebody killed the internet. Ah, it was me. Okay. No. All right, there we go. So now we've computed the numbers. It's not super sexy in that sense, but it's kind of as an example, it shows you very quickly what you can do. So now what's the problem? Yeah, right? Because if I just do dest buff, we have to get the data. So it's just like, what are you trying to do? So this is where the memory spaces kind of come in. You have to be aware that buffer is not on my host, so I have to pull it in somehow. And so I do the same sort of thing. Okay, I try to do the same thing. Bug in the slides. So A plus B, I give it a numpy, and I say empty like A because I don't want you to do anything with my memory. And then I enqueue the copy. I think I have to do a wait there because it gave me back. It's like I give you a nanny event. You haven't started or done anything with it. And then CL enqueue copy, and now I have it back, and I can check out something like sum A. It's source or it's destination. Destination source. So it figures out where your. So if I switched it back, it would go the other way. And that's kind of where the smarts are. And if you actually called OpenCL, there's different commands for where you give a flag that says host to device or device to host. But this is kind of the nicety of Python is you don't have to worry about a lot of that because we kind of know where things are. I mean, so because if I say dest buffer, it tells me that it lives in the CL world. So that's your first basic OpenCL program. It's easy, right? Nothing to it. You can play around and use different types of kernels very easily. You know, just do your multiplies, do your adds, and stuff like that. So you get a little crazy even. So feel free to. So for example, here, what's the problem with this code? Does anyone tell me? So right. So if I add that +1 there, I've just incurred a data dependency, right, on the guy in front of me. So it doesn't matter too much because A is not changing, but I also have to make sure that I'm not going to execute that last thread. So I need to say, okay, I have to rewrite. If I was using a file, it would be much easier. So if I think I need a 0 there. I need something like that, right? So that I know that the last guy, well, I can't get a GID +1, so I better figure that guy who stopped writing that code. And that's another example where you have to kind of worry about data accesses, things like that. All right. All right, so my favorite kind of example to show off is a Mandelbrot set. And let me check my time. Actually, what we'll do, we quit at 4:40. So everyone's able to get the slides. So I'll let you guys kind of play around and code this up while Travis and I switch so he can give his part of the lecture. But I'll just go through this one kind of quickly. So we have a Mandelbrot, which is something that speeds up a lot faster. And here, a Mandelbrot is basically a 2D image, and you're computing where the an iteration, and I'll show the actual calculation, how far it goes until it escapes, and it's changed color based upon that. And so you have these nice fractal patterns. And you just do the same sort of thing where you create. So this is an example from their set. If you actually you can actually go to my my example, or if I say cd a Terrel /opt /source /pi OpenCL examples. And you can see the example. It's actually this demo Mandelbrot. So, yeah, you should be able to get there. It's not letting you get. It's not letting you CD there. Is anybody getting there? Yeah. Oh, you have to do this tilde a Terrel. Yeah. So I checked to make sure this worked. So you should be able to say %run demo Mandelbrot .py. Oh, well, it doesn't like my display. But if you ran that with the display option, you would get. So basically what he's doing here, and you can look at the code and get out your IPython session and things. And he's creating a fractal, copies the memory the same way. So he creates x and y are the 2D images. So you have to give the x, it gives you 2 because you have an x and y coordinate, and it's a complex value. So you're saving your reals in x and your complex in y's. And p is going to be our what we compute into, so our output. So you do this kind of fun NumPy ravel, which, if you don't know that command, you can look it up in NumPy. Copy your buffers the same way. And here you do, so now your code, he has a little extension to make things a little bit more faster address space. And there's a lot of extensions to OpenCL if you get into it. And you do the same sort of thing. I get my global ID, my floats, and I get which guy I'm outputting, and I set it to 0. And here's just the iteration. So since we're iterating, every thread's going to iterate this guy. So this is our inner loop, and you pump it back out. You can build it, do the same sort of thing. I like to show this off. So I put together this guy in a Pi app for an APUG workshop. So can anyone tell me what's slow about that code? Nobody has any ideas? The branch doesn't hurt you that much because it's a quick branch, right? So that one. So when branches are of different sizes, that's when they really hurt. But so you got to do branches sometimes. But the big inefficiency in this code is that you're passing these big arrays, and I know what those arrays are. I can compute them, and so I have another option where I created a faster one, where you give me the X and Y, but you don't actually create arrays. So all I do is I figure out my dx dy from those variables. So now you just instead of passing arrays around of this image, I just pass what my bounds are, and I let the individual thread figure it out. And this guy turns out to be a lot faster code. It's the same sort of code, and you just change your iteration a little bit. So yeah. Yeah. Yeah, it's yeah, I meant to put it on the slide, but it's it's GitHub APUG. So I gave this at the Austin Python user group, and the examples there in the PyOpenCL. So GitHub Terrel APUG. Okay. Yeah, and so the cool thing, so I run this on my laptop, and so I say Python, and I just have a little Pygame runner, and I think Pygame, I like Pygame because it's a lot of fun to play with, and create simple apps. And you just register some execution things, and all of a sudden you can have a Mandelbrot viewer very quickly. You just run the app.py, and you get X takes forever to start up, but when it does, it tells you skip this version. So then you can't see it at all because it's if you download the code and you have Python, so you can move this up. This is all in the CPU in Python, right? There's only 6 lines of code that is. And you can see, well, it goes, but you can see the iteration count going up. If you've ever tried to write one of these guys in Python, you realize you can't do this, right? Because that size of image takes forever. And so very quickly you create an interactive like image app. So that's kind of where the whole kind of impetus for this discussion kind of started. I was at APUG and I did this, and people said, hey, you should talk about this stuff. All right, so that's all I have. And we're going to switch over to Travis Oliphant, the creator of NumPy and starter of companies and mover and shaker of the Python world. Yeah. Well, you're not up here ready, so I have to embarrass you. Is there any questions while we switch out?
cell phone interference.
Yeah.
Very nice. All right. All right, thanks, Andy. Thanks for letting me take a few minutes from the last year tutorial to talk a little bit about kind of some of the ways I see Python taking advantage of hardware beyond the CPU. I'm going to talk today about both Numba and Numba Pro. Now, Numba is completely open source. You can download it. It's just like everything else. We distribute Anaconda. One of the reasons we give away for free is so that you can get Numba easily. It does require the LLVM C++ library. Not too hard to build, but if you've ever built software, you know you much prefer to have a binary version of it than to go and build it yourself. So Anaconda can get it, download it, and install Numba, and it works just fine. He's got it on the TAC computers. You can also get it installed on your systems pretty easily. Numba Pro is a commercial product, so it's not a very expensive commercial product, but we are selling it to help, basically to help fund its development. It takes a lot of effort, as you can see, to actually drive and write code to work on modern hardware. It's a lot of effort. People are spending a lot of money doing it. We'd like to get in that game a little bit and try to make sure Python has a strong story there. But to do that, we got to fund it with selling a commercial product for now. We'd like to move some of those features into the open source space, and we've been doing that actually over time. You see some of the things that have been in Numba Pro for about 6 months, or recently in the latest release of Numba, are now in Numba itself. Things like, and I'll show them some today, things like vectorization and array expressions are now in Numba itself. So that's our goal, is to try to move as much as we can over there. But there are people out there who can pay for Numba Pro, and if you can pay for Numba Pro, please do. It'll help fund and support the project and help us continue to work. So Numba Pro is what targets the GPU and accelerators, and Numba is just targets your serial sequential CPU. So that's kind of the divide. We'll talk about both. I know that not everybody has heard of these before. Actually, raise your hand if you've ever downloaded, installed, tried out Numba. Yeah, I got a couple of people brave enough to say that. Great, okay. It's made a lot of rapid progress. Really, the first usable version was probably in November, I think, version 0.3, and it had several bugs, and you could definitely find them in your codes. 0.7.1 was just released a few days ago. It's stabilizing. There's more and more I can do without bug fixes and bug patches, but I'm not going to say that there aren't any bugs left. There's going to be bugs left. So if you find a problem, something not working the way you might imagine, let us know, because that's what's helping us stabilize it, is the examples and the use cases that people are providing. That helps us make it faster. There's a Numba users list as well. Let me talk a little bit about Numba, just its idea. A little bit about me, I guess. I don't know if everybody knows me. I used to be a scientist. I used to spend time in medical imaging. I was actually doing an MRI ultrasound combined project, and I went and taught at university, taught electrical engineering and electrical engineering, mostly in biomedical imaging, and had a lab there. Through all that, I sort of got tied into the numeric back then, and I started the SciPy project, really excited about just making a bunch of tools available to people. And so I pushed heavily in the SciPy world, and then spent a lot of time on the array object, and NumPy came out in 2006. So sort of all of that has kind of sucked me kicking and screaming into a software developer role, which is what I'm doing now more. But it's a software developer role that comes from a scientific perspective. I really want to take advantage of modern hardware, not just to do cute things like compute Fibonacci sequences, but compute them as linear filters, or unstable linear filters perhaps. But do things that matter to people, like imaging so our big picture is to empower people who are doing stuff at a high level with lots of data, and connect that to the hardware that's also growing these vectorization primitives. And there's really this big disconnect right now, and you kind of saw some of that, I think, in the talk, how difficult it is. It's PyOpenCL, PyCUDA, some of these tools are trying to make it easier, but it's still difficult, and some of that's perspective, and then some of that also, though, I think, is the tool chain that hasn't really kept up very quickly with modern era. APL, everyone heard of APL? Raise your hand if you're familiar with the language APL. Really, yeah, I like that. Great, we got a few people in the audience willing to admit that. Now, APL is a great concept, and it's been around for a long time. It still is underneath some very popular libraries like K that are used on Wall Street in a lot of banks and hedge funds. These high-level array-oriented programming techniques have existed for a long time, but kind of the rest of the computer world sort of bypassed them and went down the object-oriented train and kind of ignored this other really powerful set of ideas. And so, there's a lot of reasons for that. Money drives everything. And so we're kind of circling back around now to where hardware is really empowered by array-oriented concepts. So we're trying to kind of bring some of those ideas back. Now, in NumPy, in Python, is really an echo of APL. If you think about how NumPy, who's used NumPy in this world? I mean, that's sort of how you get performance out of Python today is by using NumPy, along with some of the tools we'll show today. But NumPy really is about array-oriented computing. I mean, the idea of array-oriented computing is to collect there's a couple of ideas. One is memory. Organize your memory together so you're not jumping all over memory, all over your RAM, trying to collect objects together. Bring it all together and do things all at once, along whole columns, along whole, we had that strided image before. You want to do operations on data that's close together. And so how you organize your data becomes quite important when you want to talk about performance. And you see on the GPU that's even more important. You've got to make sure your data is on the card. You've got to make sure that the data is accessible to the threads that are running on those data. So that's one concept of array-oriented computing. I'm not going to, why Python is important, but I think I want to emphasize one of the things on this slide. Integration. I mean, you look at the way people are taking advantage of high-performance computing, and one of the biggest challenges they face is, great, I got this wonderful little tool that can take advantage of my GPU, but now how do I integrate that with the rest of my system, my big application? I mean, that question of how do I do that is most of the effort, in fact. It's very easy to write something that'll create code that's fast for the GPU. Well, straightforward. Easy is probably not the right word for that. It's straightforward, using some high-level language. The more difficult question is how to connect that to all the other tools I've already got written that are producing the application for my end user. The GUIs, the visualization, the plotting libraries, the mapping libraries, all the other libraries. Every organization out there has a host of code that you're relying on in order to connect and solve your problems. And you want to figure out, how do I take that code, integrate it with something that speeds up the critical portions and moves that to the GPU. And how do you do that well? That's really one of the challenges. And what I'd like to say is Python can be a big part of that story. And so I'm going to first talk about Numba because I think it's a sea change. I mean, Numba provides you an ability to think differently about writing performant code. For most of you here, if you want to say, I got to write performant code, you probably think, okay, I got to pull out my C compiler, right? Or if I'm not pulling out a C compiler, I got to at least generate C code so that my C compiler can take that code, right? So what I want to first of all point out and emphasize is that that's no longer necessary. You can write Python code that is as fast as C code because we have a Python compiler that takes Python syntax when you have typed containers and creates optimized code, just as if you'd written in C. So that's what Numba is about. It's about doing that, breaking that speed barrier, allowing rapid iteration and fast code execution. How does it do it? Well, so every C compiler, you have a front end that goes to an intermediate representation. So the front end parses the syntax, the ASCII syntax, goes to intermediate representation. And then that intermediate representation is then compiled to machine code. With Numba, we just bypass that front parser, and we go right to the intermediate representation from Python representation. Go right to it and generate the machine code. And in fact, if you've ever used CLang, who here uses CLang? If you're you use Xcode, you've used CLang. It's also available on Windows and Linux as well. The CLang compiler targets the intermediate representation that we target as well. So we benefit from any improvements to the back-end code generation that project promotes and provides. So the technology behind Numba is basically to use this LLVM library, which is this low-level virtual machine. It's a horrible name. It's not really the virtual machine aspect of it. It's the low-level intermediate representation. It's LLIR, maybe. It's the IR that matters, that intermediate representation. We target that, and that project, which is supported and sponsored by a lot of the hardware manufacturers, NVIDIA, Apple, ARM, Intel, every one of them have a LLVM project that generates code from that IR. So they can worry about making fast code from the IR. We just target that IR. And it makes compiler writing, it actually it allows you as a Python developer to become a compiler writer. Literally, I went to Dave Beasley's class in last June. I think he's tweeting about some things that happened during that class too. I lost my bag and he found it on a bus using public data from the bus front lines. It's become a popular topic for him today. But at his compiler class, we basically wrote a compiler in a week, and really it wasn't that long to do, because you could, with LLVM Pi as the back-end code generator, you could create machine code relatively straightforwardly from whatever language syntax you liked. I mean, it wasn't that hard to create a parser with all the tools in Python. It really isn't that hard to create a simple compiler. Now what's hard is making a robust compiler that gives good type information to somebody who makes a mistake. How do you help somebody who makes a mistake actually get an informative piece of information rather than just blow up and have the program die? That's a little harder. That's sort of a usability question that takes a little bit more time. So that's the idea. Here's an example. So we take a Python function like this sync function, And then there's really two APIs to Numba, just JIT and AutoJIT, and they'll see both of those. JIT, you give it a string or some other specification of what the types are for the input and output. And actually, it's only the input type that's necessary. If you look at this Python code, syncx, you'll notice there aren't any types in Python, although whenever it's called, it is called with a typed object. Python is strongly typed. It's just dynamically typed. You don't have to specify the types when you write code. So it's like you're writing templates, really. And so I write this template of code I want to execute when it receives an object. I have to specify to the compiler what type should the input be. And then Numba, the JIT decorator, can understand it can do type inference to determine what the output should be, but I can specify it as well if I like in this approach. And that will generate for me a machine code version of that function. I'm putting it in this simple case, you can actually write out what that LLVM code looks like. You don't have to care, right? The fact that it generates that internal representation is not really critical, but it just illustrates that that is the same internal representation that your C compiler would take a C expression and also produce in order to get binary fast code. We're doing exactly the same thing. So I emphasize it just to try to kind of convey and hammer on this notion that when you write Python with typed containers, meaning NumPy arrays, you can generate code that's as fast as if you'd written C. It's the same code path. And you get code that can then target x86, ARM, and with the LLVM project, you can also target PTX backend, which is NVIDIA's assembly for their GPUs. And eventually, we'll also be able to target AMD's GPUs, and we're also able to target Mike's because that's basically threaded x86 code. So this is all possible with this compiler tool chain, and it makes kind of programming for the low level, it just changes your perspective entirely. You start thinking differently about everything. You know, this past year has been a real exciting one for me because I've spent my life wrapping a whole bunch of C code and writing a whole lot of C code to make Python faster. And I sort of realized that all of that could be done completely differently. All that could have been rewritten differently, and I'll show you a couple of examples of that. Not saying that it should be at this point. I mean, there's no need to throw out code that works. But new code and code you're writing in the future doesn't necessarily have to use the same paradigms and patterns. And it turns out I think there's a lot of advantage to doing it differently. So just a simple, I'll actually show this in a notebook instead. Here's just an example of how to use it, and I'll try to go fairly quickly so we can get to a little more interest in some of the GPU stuff. What's that? My flow doc is immortalized, that's true. I'll close that. Thanks, that's a fun IRC chat. Here's an example of how to use it. I used the decorator before, but a decorator, you know, is just a function that takes a function and returns another function, right? So I'm going to use that in order to actually explicitly get a reference and keep on to the Python version. Then I can also get the faster version as well. So here I've got two decorators, JIT and AutoJIT. You notice the difference is AutoJIT doesn't take any type information. AutoJIT just grabs the function and then basically puts what's called, I call a call site. That was the term that IronPython used. It's just a function that waits and sees what it gets called with. And once it gets called, then it knows, oh, I know the types now. And now I can generate code that works for that type and then store it and cache it. And if I get called again with a function with that object, I'll call that old code. Otherwise, if I get called with a new type, I'll generate new code for that type, new function, new code. So there's a little bit of overhead on dispatch for AutoJIT that's not there with JIT. Because with JIT, you're saying generate this code and only this code. But then good luck if you call it with a type that's not understood. You know, that's now your problem. AutoJIT is a bit easier and with a slightly bit of overhead. Here's some examples. They show exactly the same result, except the flexible sum with the AutoJIT can be called with a different type, and it does the right thing. It generates code that does the conversion correctly. Now, when you look at the timing of these codes, so sum is the Python version, 460 microseconds per loop. Fast sum, you can see, is 921 nanoseconds per loop. So it's about 450 times faster, right? Just with a single decorator. And if you look at the NumPy sum, which you know is hard-coded in C as a pre-computed C loop that you then import as a dynamic shared library, it's even faster. The code I just generated is faster than that, which isn't also too surprising if you know a little about NumPy, because there's some overhead associated with calling through these various Python C APIs in order to get to the raw ultimate loop that gets run. So it's you'll see people talk about this sometimes. You know, I can beat NumPy. Well, that's true. NumPy is pretty good, but it certainly isn't optimized in across the spectrum. In fact, trying to think about how to move NumPy to the GPU really pushed and started on this whole experiment that's led to Numba and to the new product called Accelerate or Numba Pro. All right, so the speed up even gets higher if I take like image processing. Image processing code, like this filter. You'd never think of a nested for loop, 4 nested for loops in Python. Are you kidding? You know, you can just see the horror on somebody's face. What are you doing? But with JIT, hey, no big deal. It's fine. It actually produces really nice code. So I can think at a high level and still do my programming with for loops. I don't have to be a vectorization genius to write code. I still think it's useful to do vectorization because vectorization conveys information that then a compiler can use to target GPUs, other things, for example. So I'm not ready to throw out vectorization. I think it's still a useful concept and one we should be promoting. But it also can be hard to teach, and sometimes it's easier to do this. And then I just have an example where I'm grabbing an image. And you can see the result. Python took 2 seconds, Numba took 2 milliseconds. So over 1,000x speed up on that. And so I can do real-time image processing with Python code, with a simple decorator. So the intent is to really enable the ability to take kernels, to write little kernels, optimize your pieces of Python code in whatever large system you have. I think there's a lot of application for that in people's large systems where you need to write a little kernel or something that you want the user to write Python, but you want it to be fast. Numba is perfect for that. It really does a great job. Now, what the key behind making this fast is the fact you have a typed container. The fact that everything here is a NumPy array, which has been typed for over 15 years. We've had typed containers for a long, long time. The PyPy project was essentially trying to make Python fast with these arbitrary containers, with who knows what's in them. And we still want to make that fast sort of at real time. That's a much harder problem, right? But as technical scientific users, we don't need that. We can just make Python code fast with containers we know about. So that's what Numba provides, is that fast compiler for those cases. And we're adding things like typed lists and typed dictionaries as well, so that you can speed up that kind of code also with Numba. All right, so here's the example with Mandelbrot image, and it just shows it produces it in 16 milliseconds. The speed up's about 130, 150. Previous examples have shown this to be a much faster speed up, but a lot of that was due to a slow version of AutoJIT that was in previous results. So we're kind of slowing down the Python version and speeding up the non-Python version to get that speed up. Not intentionally, that was just the reality. All right, so that's Numba. I want to show one more example because it illustrates what you can do with a new feature called Vectorize that's in Numba now. Anybody heard of ufuncs in Python? NumPy has these things called ufuncs. Okay, ufuncs are universal functions. It's pretty straightforward actually, but any Python function, anything in Python that you're using, let's do an IPython shell. So if I look at import NumPy as MP, so that's a ufunc. What ufuncs do is they take arrays and they return arrays, and they take a function and apply it element by element to every term in that array to give you the output array. And so they're very fast. It's the equivalent of doing like math.exp on a list for x in some list, right? For 1D, but it also works for 2D, 3D, and so it's sort of the equivalent of doing that for arbitrarily possible shapes and sizes. And it's got some broadcasting rules that are nice. So if I take a simple array, then I can do, like, I can execute a function and get an array output. Okay. So I've always wanted to make new ones of these. There's a bunch of built-in ones in NumPy, and one of the first projects I did for SciPy was actually create SciPy Special, which is like 150 other functions, like the Bessel function and the Mathieu-Dawson integrals and error functions and ERFCs, like all the special physics functions, as many as I could find, and make those ufuncs. But it was kind of a hard project because I had to make C code and I had to link in Fortran code, and it was kind of this big pain. So I've always wanted to say, why can't I do that in Python? Why can't I write Python code and also produce one of these ufuncs? Well, you finally can because of this Vectorize in Numba. So if I look here, and so I just grabbed the actual same algorithm out of SciPy Special. It's got basically a Padea approximation to the Bessel function, and different depending on where the x factor is. So these are just polynomial evaluation functions. You see they're jitted. They take a a coefficient vector and then a function value, and one that there's two of them because one of them assumes that the coefficient vector has a 1 at the beginning, so just for optimization purposes. So it's the same algorithm. Here's the coefficients of the polynomials stored as arrays, and then here's the function jitted. So J0 as a scalar function, you can see it's just if x, I do some tests, I look in different variables, there's some constants defined, and I do this polynomial evaluation. Fairly straightforward, looks a lot like the C code and CFEs. And then from numba.vectorize import vectorize, there's a vectorize decorator that I can say, now make me a ufunc out of this, take this kernel, and then the F8, vectorized kernels can have different versions for different types. So make me one that has a type for doubles going to doubles. And then that ufunc object will be able, when it takes integers or floats or other things, it'll cast them to doubles, then call that low-level function for me. So it's basically the equivalent of the SciPy special J0 function. So that's here, ss.j0 is just the SciPy special function. So you can see that I get basically exactly the same performance, a little faster actually. My simplified, very easy to write Python code now has a ufunc in Python. So you can basically look at the entire SciPy special directory with its reams of Fortran and C code. All of that can be replaced with a few Python lines and numba. I'm not saying that we should do that, but it could be done. And it's kind of fun, and it gives you the same result. And I would say this is a lot easier to maintain and to understand and to teach and to show somebody how to dynamically, iteratively do this. I can certainly also take away the decorator. It's all in Python, so I can use Python debuggers. I can walk through the code. I can make sense of it with somebody, and then just add the decorator to speed it up, make it fast. All right, so that's numba. That's the idea of numba. It's a powerful idea. I think it's one that sort of changes your perspective quite a bit, and so it takes a little bit of getting used to. Like, really? That's possible? Man. I mean, it should empower everybody. So those who are C programmers may go, dang, now the guy down the road who doesn't know C can write faster code than I can. So hopefully that doesn't make you nervous. There's still a lot of neat tricks and things you can do to make your code faster that'll still require a lot of understanding. So don't get too nervous about that. All right, so array expressions, this just shows, I showed vectorized, but array expressions are the idea that you can write vectorized code and it produces actually looped code from those vectorized inputs. The goal is so you can take these array expressions and eventually target those to the GPU as well. In fact, you can now, but the code that's being generated isn't necessarily optimal. We're still working on making that better. It targets the GPU and moves part of the code just to different threads and does it automatically. But that's a hard problem, and we're making progress on it. And this is the idea of vectorize. So Accelerate is a new product. It's an add-on to Anaconda. So it is a commercial product. It's $129 per user. It's sold as a runtime license. So it's not a developer tool. Actually, everybody who uses Accelerate has to have an Accelerate license. That's the way we're selling it right now. What it does is it takes numba code, and instead of producing just CPU code, it also produces code to go on the GPU. And it can take, that vectorize example is a good one. So it could take that special function, and as soon as we define global constants, which isn't defined yet, so I can't show you that, but as soon as we define global constants, you can take that vectorize function and actually run it on the GPU. And so take an array of 1,000 elements and have each of those run on a different thread and do that compilation, do that algorithm that was just shown on each of those threads. To do that efficiently, you're going to have to make, if it's making reference to global memory, you're going to have to move some of that memory to shared memory and actually do it a little bit more intelligently. So, you can do things simply and by default, and you get one set of performance. To really get big performance out of GPUs, you have to still write code that understands the hardware. And so that's why we've introduced in this Accelerate product something called CUDA Python, where you write CUDA code just like you do in C, except it's Python code. And you just decorate and write CUDA JIT, and then it creates the same thing. Before we get into that, probably the easiest way to get acceleration out of your code is to use this p-range concept. P-range just allows you to basically take the block inside of p-range, and it'll run that block on different threads. As many CPUs as you have, it'll create that many threads and run that block across it. So it immediately gives you no JIT no GIL, no global interpreter lock. It'll run it across all those threads. There's some caveats here, right? I mean, kind of smooth over some questions you may have. I'm generating code here from Python. Okay, what happens if I can't generate machine code out of it? Like, what if I'm making some call to a dictionary, or I'm making some call to some arbitrary library? So Numba, what it does is it'll actually insert Python CAPI calls. So it'll basically take pretty much any Python code. There's a few, I think generators are one that it doesn't do yet. But it'll take pretty much any Python code and produce CAPI calls that's equivalent. Now that won't work with p-range, right? If you have CAPI calls in the middle of your block, then it'll raise an error because it'll say you can't depend on the CAPI because I have to throw this on a different thread. So there is this notion of no Python context and Python context. By default, it allows a Python context, but you can specify in the decorator make it a no Python context in order to raise an error if it's trying to insert Python magic essentially in your code. Okay, so CUDA Python looks something like this, and I'll just show a couple of examples basically, and I think that's all the time we have. It's writing, the thread IDX. He showed from OpenCL thread IDX, block IDX. CUDA has the same constructs. I'm actually not an expert on this, and so I need the folks that are developing this know a lot more about the GPU than I do. I'm still learning, actually, so I'll get tripped up from time to time. But I understand the concepts, and you basically write the same code, and you see that in red is basically what the CUDA specific concepts are. So you write your kernel. This is an example of just a simple kernel that does, it maps that individual, you can see the DSTI equals source I times scale. Each of those subroutines are run on a different thread when that moves to the GPU. You can see the grid block. Actually, you don't see the definitions of grid block in that example, but that's how we, in CUDA Python, specify how you're laying out the thread units. In OpenCL, it was with that greater than signs. Basically made a subroutine call and parameterized it with these greater than signs. Here you parameterize it with this grid block. Here's a more complicated example. In red are all the CUDA specific calls. CUDA shared array. What CUDA shared array allows you to do is allocate shared memory. Instead of you have global memory for the GPU, you can allocate shared memory shared by some of those blocks. And that's really important to get performance if you're needing to refer to neighbor values. If you just have a very embarrassingly parallel thread, you can do it quickly and easily, and you don't need to allocate shared memory. If you don't, you need some, essentially, it's basically programmable cache. If you need that so that you can store data there and use it during a loop, it really makes a huge difference. Otherwise, your code's going to be going back up to the global memory, and that fetch takes a lot longer relative to the compute power than even on a CPU. And so you can see that's basically moving, SA is moving data from the larger array into that local array. That's basically what's being done in that first for loop. And then you sync the threads, use some of the threads to move data to the shared memory inside of this loop, and then you actually do the calculation from the shared memory. Then you sync threads, and you go back. That code, and then you see the code that calls it, basically set up a stream. You move data to the device. So I have these arrays, A, B, and C, and I create sort of mirror arrays, just opaque pointers to those arrays that are really, so the DA and D, B, and DC are really on the device. And then I call my CUDA function and then take the result, which is stored in C, move it back to the host. So it's very similar to what you might write with CUDA C, but it's a lot easier to sort of write, and it's a lot easier to get working. And it performs. We're basically probably presently we're not generating code as about 33%. The best one example I've seen is 10% of CUDA C, basically somewhere between 10% and 70% of the speed of what the CUDA C compiler is doing. We haven't really done a lot of optimization, making sure we're generating the same PTX code. But we certainly can, and there's a couple of reasons that's the case. A lot of it has to do with the arrays and the way those arrays are laid out with multiple strides and shape, and the way the kind of the details of the array layout is slightly different than when people don't use NumPy arrays in CUDA C. They sort of build their own concept of an array, and there's some optimizations that take place there that we're not able to do because of the generality of NumPy. But there's ways to improve that. Here's another example I'd like to actually run. Don't have to worry about reading that. It shows you a couple things. One, it shows you that CUDA Python is low-level CUDA. It's not as low as C, it's not low as CUDA C, but it still requires you to write sort of constructs that aren't. You have to understand a bit about the hardware you're targeting. You have to understand these idea of these threads that are running. You You have to understand that you have to programmatically tell it when to move data where and to sync threads at appropriate times. And if you don't do that, and just sort of, the ideal is you have array programming and that all happens for you magically. We're not there yet, right? That's a goal, and I don't think you'll ever be able to, as Andy said, get away from just thinking in parallel. Like if you think in parallel, you'll write faster code than if you don't. And so what CUDA-Python does is give you tools to think in parallel with Python syntax. So I have this running basically on a Amazon instance. Unfortunately, the GPU examples, Accelerate is installed on the TAC computers, but these GPU examples rely on CUDA 5, and the TAC computers only have CUDA 4.2 installed. So I just this morning installed CUDA 5 on this AWS machine in the cloud, and I'm able to run this example now. And if you look at, there's a couple of versions of it. We have a Numba version, right? You can see that it just is. It's written in Python, and it compiles it down to C code. A big part of it is writing this CND Numba. This is the cumulative normal distribution function, and a common approximation to it, basically. So we're auto-generating that function. That's getting called during this Black-Scholes computation. It's just computing it multiple times. So that's the Numba version. If we look at the NumPy version, I think that's the Black-Scholes Pi. It does the same thing, same code, except it just uses NumPy. So there aren't any loops here. It just uses NumPy vectorized calls to take ufuncs and express them. It makes this new ufunc called CND. So there isn't a loop inside there or anywhere. It just calculates it entirely with NumPy. Okay, so you can see that example. And then the Black-Scholes CUDA example, a little more involved. Use CUDA-JIT to take this same code, but now it's going to, device equals true, inline equals true, means it actually takes this subroutine, moves it to the device so that it's accessible as a subroutine from the code that's compiled in the main routine. It actually inlines that. Then you see CUDA-JIT here. Slightly different interface. This is just another way to call JIT. You can give it the argtypes as a keyword argument instead of a string with the type versions. Just another, it's an API. Notice if I just give it argtypes, it does, there is no return type, but it does type inference to determine what that return type would be. On CUDA-JIT calls, there is no return type. It's always none. And all the returns have to be done on arrays that are passed into the function arguments. So you can see the result, put result is all there. And then notice that there isn't a loop here as well. I just use that I index. So that I determines which thread this runs on. And this code will basically run on each thread when I call it. So the calling code has to say, well, how many threads am I going to use? How do I take this kernel and then split that on the threads? And so that's what this code is doing. You basically see, well, it's calling Black-Scholes, Numba, and so forth. But here's it takes and creates this device result, connects it to a stream, because it's this asynchronous programming going on. I have a stream, and then I have, okay, now what am I going to do in this over here in this accelerator? I'm going to first, copy data, and then I'm going to copy another piece of data, and then I'm going to, in a loop, number of iterations it's going to call, and that's just to give more time, basically. Otherwise, it happens too fast. This is how I call the grid dim, block dim, and stream. That's how I tell it which stream to associate this function call with. The grid dim, block dim are allocated here. So the block dimensions is 512 by 1. The grid dimension depends on the size of this n. So it takes the array size and basically maps it so that every element of that array is calculated on a different thread in the GPU. So, and then it just executes this call with the data, and then it takes the results and moves them to the host. Because they're still sitting on the GPU when that's done. They've got to be copied back to the host. So a lot of GPU benchmarks and timing is really, are you going to get enough speed up for the code, for the time you spend on the code to justify the cost of moving the data there and bringing it back? And in fact, that's a lot of figuring out good benchmarks, is figuring out where does that, and figuring out whether you can use the GPU, is how can I get a processing stream and actually just keep the data there? It's the same problem that actually exists in parallel computing everywhere, is like data has mass. I can't be moving it around. I got to move code to data. So the real question is, how do I do that? How do I express the code I want to move and write it so that I can move to those data? I think it's actually going to require us to rethink how we actually generate code from high-level expressions. That's part of actually a project called Blaze that we're working on. You just have to sort of think, a lot of times some of the trouble is fitting through sitting a round peg in a square hole, or the other way around. We're trying to do this, use a common patterns we used before, and still shove them into the way we're thinking, the way we previously thought. There's reasons for that. Again, it goes back to integration. A lot of our tools still need those old patterns. We can't just start anew. We still have to have all these libraries that work. We don't want to rewrite them all. All right, so if I run this code, so that's, you can just see the example. I just ran that earlier today. Black Shoals, do the number example, see if that works, or gives me an error because I just logged in and didn't set some environment variable right. What that should show, basically the NumPy result, if that's 1x, then the number result, which just did the loops itself, basically about 2 times faster, 780 seconds, and the CUDA-Python result was 20 times faster than NumPy result, about 10 times faster than the CPU result. And that's pretty common. You'll see that quite a bit. GPU examples, somewhere between 5 to 10 times, 2 to 10 times. If they're not, they could be slower. If they're slower, it's because typically you're either not using shared memory very well, it's spending too much time copying data. Basically, the threads are idle. You have all this compute power sitting over there. It's amazing to me how much compute power sits on a GPU. But it's idle. The problem we have, most of our CPUs are idle. Now most of our GPUs are idle too. It's a lot of effort. All right, so that's pretty much what I wanted to show. There's a few more examples here, but if you have questions, we can talk about it. Yeah, sure. Let me, I can just put them into, you have them on GitHub?
No, you have them.
Well, I just put them in the same place your stuff is so that people can go back and,
Yeah.
I'll just put it where his code is for this tutorial, so that it's the same place. Yeah. Yeah. So you can still use those tools because that's one of the nice things. We're actually working pretty closely with NVIDIA on this. We'll be showing off some of the new features of Accelerate in the GTC conference next week. We're giving 2 talks in a hands-on lab actually. And you can use some of those tools still, but absolutely integrating some of those tools at a high level. And we're actually working with them about actually improving the APIs so you can do things like resource allocation. One of the problems is dynamically knowing how many resources you have on a GPU. They haven't exposed that API, so it's sort of run it and see if it fails is kind of their their approach. But you'd like to be able just to query and say, can I schedule this many blocks on this card and get back, no, this is the minimum resources available. So those kind of things are hopefully going to be coming out as CUDA improves and as this code improves. So yeah, that's great idea. I think there are a lot of things we could do that improve the connection. Yeah. Yeah, no, I haven't done that. I imagine it would be similar. But I haven't done that specifically. You can get to it's the same. It's the same thing it's doing, and actually the same author, same guy wrote both of them. But but it's quite different technology, right?
Mark was supposed to be here, but he had to go back to England. So.
Yeah, and I should emphasize actually it's Mark Florisson and Sue Quan Lam that have done the bulk of the work on these projects. So. Any wrapper. So
Yeah, I don't want to use the decorator instead of some other API where I can call a third-party tool.
So you want to call what's an example of third-party tool? You want a function from somebody?
Yeah.
Well, so a decorator can be just used as a function. You can grab that function and just call it. Yeah, you don't have to decorate it. That's just one approach. Just like I did in the FastSum example, just use the decorator as a function and hand in the other function. Yeah.
So I guess we're out of time, but I just wanted to, you don't have to leave, I guess. I don't know if we're kicked out of the room or not. But announcements, thank you for coming. Thank you for sticking around. I'll probably leave our machines up for a day or two so you can play with this stuff more if you like. Survey, take it now if you have time. They really need the information. Volunteer. There's our emails if you want to follow up with more questions. There's the slides that I gave. Your slides are kind of all over, so I don't know if we'll get your slides together, but maybe I'll try to get them together.
I can. My slides are, I have this one key file. I'm going to PDF.
Yeah, and then that APUG repository is where the code that I showed off was. So, thanks a lot.